Red dwarfs are the most common stars in the universe, and not one has ever died. They outnumber every other kind of star combined. They have burned since the young universe, and none has run out of fuel. They are also the faintest stars we know. A red dwarf can be hundreds of times dimmer than the sun. It burns its hydrogen so slowly it hardly spends anything. That is why it will still be shining when every bright star is gone. So what happens when the last star dies? Before we begin, if this slow, quiet science is something you love, a gentle like or a soft tap on subscribe means more than you know. It keeps this little universe of ours alive. Now, let your eyes go soft. We go to the last star, to the cold thing it becomes, and to the final explosion the universe will make. The last star still burning will be the smallest kind of star the universe knows how to make. Not the sun, not any of the bright points you can name on a clear night, not one of the great blue-white stars that light up whole regions of the galaxy. All of those will be long gone. The one still glowing at the very end will be a red dwarf, a dim little ember, maybe a tenth the weight of the sun, the kind of star you cannot see with your eyes even when it sits close by. It catches us off guard the first time we meet it. Somehow we expect the biggest, brightest stars to be the lasting ones, the ones that hold on. They are the first to go. And when we go looking for the reason, we find that the amount of fuel a star holds barely enters into it. What quietly decides a star's whole life is how fast it spends what it has, and whether it can ever reach all of it. Two simple things, and between them they settle which stars flare out young and which ones are still here at the end of time. Let's follow the spending first. A big star does begin with far more fuel. A star 10 times the mass of the sun starts life with about 10 times the hydrogen. You might think that head start would let it live 10 times as long. Instead, it tears through everything in a few million years, while the sun goes on for something near 10 billion. 10 times the fuel, and gone 1,000 times sooner. The gap is so wide it almost feels like a mistake in the arithmetic, and the thing that opens it is pressure. Gather that much mass into one place and the core is squeezed far harder. A core squeezed harder grows hotter and denser, and a hotter, denser core fuses at a rate that has to be seen in the numbers to be believed. The star pours out light because it is racing through itself, and it races because the weight bearing down gives it no other option. The brilliance we love in a giant is really the sight of a star spending its whole life in a hurry. So the giants drop out of our search almost at once. They are magnificent, and they are gone in a moment. A star blazing across a nebula in some photograph has, by the long reckoning of the cosmos, nearly finished before the picture was ever taken. The far future was never theirs to hold. It falls instead to the faint ones that hardly seem to be burning at all. There is a real question hiding under all this, one that people who study stars had to face directly. How can anyone speak with such confidence about a death no one has ever seen, that no one will ever see? The answer is that a star is not a mystery so much as a slow, obedient piece of physics. Weigh it, and its whole future falls into place. The mass sets the pressure in the core. The pressure sets the temperature. The temperature sets how fiercely the hydrogen fuses, and that in turn sets how brightly the star shines and how long it can keep it up. Each step follows from the one before with almost no room to wander. So when the calculations reach a red dwarf and return a lifetime of trillions of years, the number is not a guess dressed up as a fact. It is what the physics of every star we can watch tonight, wound slowly forward, quietly insists must be true. Then comes the second thing, and this is where the real surprise waits. Whether a star can even reach its own fuel. Here the sun, which we picture as steady and generous, keeps far more than it ever manages to use. It fuses hydrogen only deep in its core, in the hot, crowded center where the pressure runs high enough to matter. Wrapped around that core is a thick outer region that carries heat the way a still room carries warmth, one layer passing it gently to the next, while the material itself stays more or less where it is. The hydrogen resting out in those calm outer layers never makes the journey down to the fire. It waits there, untouched, through the entire life of the star. When the sun finally begins to fail, it will not be because the hydrogen has run out. Most of it will still be sitting there. The sun will fade with its tank still largely full, for the plain reason that it could never reach past its own core. There is something almost touching in that. A star dying beside a supply it was never able to spend. A small star never runs into that wall. It is stirred all the way through, from the surface right down to the middle. Rather than a quiet blanket lying on top of a burning center, the whole star rolls over slowly, the way a thick soup turns on a low flame. Warm material lifts from the core. Cooler material sinks in from the surface, and over immense stretches of time, the entire body of the star drifts down through that hot center and back out again. Fuel from the far edge is carried inward to where it can finally burn. Spent material is carried back out to make room. Nothing is left stranded in a corner it can never leave. A red dwarf comes close to burning every last bit of hydrogen it owns, not only the small share that happened to begin near the middle. And there is a second gift buried in that constant stirring. As a star fuses hydrogen, it slowly fills with the ash of the reaction, the helium left behind, and helium does not burn as easily. In the sun, that ash settles and clogs the core, choking the fire from the inside long before the fuel is truly gone. In a red dwarf, the churning never lets the ash gather in one place. It is swept away and mixed back through the whole star, so the core stays clean and the fire keeps finding fresh fuel for far longer than it has any right to. Hold the two ideas together and the whole picture quietly turns over. A red dwarf spins slowly, because its small mass rests on the core with a light touch and the fusion only creeps along. And it reaches everything it has because it keeps folding its entire supply down into the fire. A slow burn, and almost nothing wasted. That pairing is what buys the staggering span of time. The sun spends fast and holds most of its fuel forever out of reach, and lives 10 billion years. The smallest red dwarf spends slowly and wastes almost nothing, and lives something close to 10 trillion. 10 trillion years. The words come out easily and mean almost nothing to us, so let's set them against the only clock we have. The universe right now is about 14 billion years old. 10 trillion is roughly 700 times that. take everything that has ever happened since the beginning, every galaxy that has turned, every star that has lived and died, every creature that has drawn a breath, and all of it fits inside the first sliver of 1% of a single red dwarf's life. We are not near the middle of the story of stars. We are in its opening moment. Which brings us to the strangest fact here, and it is a very quiet one. No red dwarf has ever died. Not one, anywhere, in the whole history of the universe. They live so unbearably long that even the oldest of them, lit soon after the universe itself began, have burned through only a thin sliver of what they hold. Every red dwarf that has ever formed is still out there tonight, still glowing, barely touched by age. So everything we say about how a red dwarf ends, we are not recalling from anything we have watched. We are reading it out of the physics, describing something the universe has simply never gotten around to doing. Every death of this kind still lies ahead of the present moment, waiting in a future so distant the stars themselves have not reached it. And if the last star will be one of these slow, patient, almost untouched embers, a question opens on its own. These stars are still being made, or they were until lately. Somewhere ahead, the making has to stop. So which runs out first? The stars themselves, or the material left to build new ones? The universe is making fewer stars now than it used to. Not a little fewer, far fewer. If you could stand outside the whole thing and watch it work, you would see a place that has already passed its brightest season of building and settled into a long, slow decline. The great age of star formation is behind us, and it is not coming back. That is a strange thing to learn, because from where we sit, the sky looks busy enough. Stars are still being born in the clouds of our galaxy right now, tonight, as you listen. But we are like someone who wanders into a party as it is winding down and assumes it must always have been this quiet. The room was fuller once. Much fuller. We simply arrived late enough to miss it. And we can say this with real confidence. But how could anyone measure the birth rate of the entire universe across all of time when a single star takes millions of years just to form? The trick is one of the loveliest gifts in all of astronomy. Light is slow. It travels fast by any human measure, but the universe is so vast that light from distant galaxies has spent billions of years crossing the gap to reach us. So when we look far away, we are also looking far back. A galaxy a billion light years off shows us how it looked a billion years ago, not as it is today. So the sky is not really a picture of the present at all. It is a stack of moments, near and far, laid one behind another. The nearby galaxies show us recent times. The distant ones show us the deep past. And by gathering galaxies at every distance and sorting them by how far their light has traveled, we can lay out the history of star formation almost like turning back through the pages of a very long book, reading how quickly the universe was building stars at each moment along the way. When astronomers do this, one thing they look for is the particular glow of newborn stars. The youngest, most massive stars burn hot and blue and pour out ultraviolet light, and they live only briefly. So wherever you see that ultraviolet glow, you are seeing fresh star formation, caught in the act. Much of that light gets soaked up by dust and re-emitted as a warm infrared haze, so the full accounting takes both the blue and the infrared together. Add it all up, across hundreds of thousands of galaxies at every distance, and a single clear shape emerges. The shape is a rise and a long fall. In the early universe, star formation climbed steeply. It reached a peak when the cosmos was only a few billion years old, somewhere around 3 or 4 billion years after the beginning. And then, having crested, it began to slide, and it has been sliding ever since. That peak sits about 10 billion years in our past. The universe was lighting new stars several times faster then than it manages today. By one careful reckoning, the rate now runs something like 9 times lower than it was at the height. It is easy to miss how gentle that decline is, because it does not look like a collapse. There was no catastrophe, no single night the lights began going out. The universe simply eased off, the way a fire that is no longer being fed keeps burning brightly for a long while on the coals it already has. From inside any one moment, nothing seems to be ending at all. A galaxy 10 billion years ago would have looked much like ours, full of young stars, its people, had it any, with no sense of standing at a peak. The decline only shows itself when you step back far enough to see the whole curve at once, and that is a vantage no one living inside the universe was ever meant to have. Let those numbers settle for a moment. If the universe were a person with a long life, the busiest, most fertile years, the stretch when nearly everything was being built, would already be well behind them. More than half of all the stars that will ever exist have already been born. We are not living near the dawn of the cosmos, in its rush of creation. We are living in the calm afternoon, after the great work is mostly done. There is a soft irony folded into that. We tend to imagine ourselves as early, as newcomers on a fresh young world beneath a fresh young sky. In one sense, that is true. The universe has an almost unimaginable future still ahead. But in the specific business of making stars, we came late. The fireworks that filled the young cosmos had already faded to embers before the sun was ever lit. Our own star is a child of the quieter years. And being a child of the quieter years carries a quiet consequence. Each generation of stars leaves the next one a little richer in the heavier elements, the carbon and oxygen and iron forged in stellar cores and scattered when stars die. The very first stars had none of that, only hydrogen and helium. By the time the sun formed, billions of years of earlier stars had seeded its cloud with everything heavier, the same atoms that would later become rock and ocean and the iron moving in your blood as you lie here. A universe in a hurry to make stars is also a universe still assembling the ingredients for planets and for life. We arrived late enough that the shelves, though thinning, were finally well stocked. Knowing the rate has dropped, though, does not yet tell us why. A slowing rate could mean many things. Perhaps the universe is simply pacing itself, and the building will pick up again. Perhaps it is running low on something and cannot. The curve alone cannot say. To understand whether this is a pause or a true decline, we have to ask what stars are made from, and whether that supply can ever be refilled. Stars form from cold clouds of gas, mostly hydrogen, drifting in the space between the stars. A cloud grows dense in places, collapses under its own weight, and warms until fusion catches and a star ignites. So the question of how many more stars the universe can make becomes a simpler, almost domestic question. How much cold gas is left in the pantry, and does anything ever restock the shelves? Here the news turns sobering. Galaxies have been using up their cold gas steadily, spinning it into stars faster than fresh supplies come in. New gas does still fall in from the space around them, drawn by gravity, but across the universe that inflow has been thinning. And the deeper reason is one we will keep meeting as this journey goes on. The universe is expanding, and that expansion pulls the great reservoirs of matter farther apart, stretching the distances between galaxies and the loose gas that might have fed them. What was once within reach drifts slowly beyond it. So the shelves are not being restocked the way they once were, and much of what remains is scattering out of reach. Each galaxy is, in a slow and gentle way, spending down an inheritance it cannot fully replace. The building has not stopped. Our own galaxy still forms new stars, about 1 or 2 suns each year, a modest trickle compared with its youth. But the direction is set. Less gas, fewer stars, and a sky that will keep dimming across spans of time we can barely name. And yet even this does not quite reach the heart of it. Running low on gas would be one thing if the gas a star used simply returned to the clouds when the star died, ready to be gathered up and lit again. Some of it does come back, but not all of it. Every time a star dies, a portion of its material is locked away and taken out of the cycle for good, kept from ever forming a star again. The universe is not only spending its fuel. With each generation of stars, a little more of it is quietly set aside where nothing can reach it. Which is where we have to look next. Not at how fast the gas is being used, but at what happens to it when a star is finished with it, and why so much of it never comes back. When a star dies, most of us picture an ending, a light going out. What happens is closer to a handing back. The star returns much of itself to the space it came from, spilling gas outward in slow winds or in a final throwing off of its outer layers. And that returned material drifts back into the clouds between the stars, where in time it can help make the next generation. Death feeds birth. The universe has been recycling its stars this way since the very beginning. So you might expect the cycle to run forever. A star lives, a star dies, its gas comes back, a new star forms. Round and round, no ending in sight. If that were the whole story, the universe would never truly run out of stars, only pause between them. But the cycle has a leak in it, a quiet one, and it changes everything. The leak is this. A dying star never gives all of itself back. It always keeps something, a dense core at its center that the return never touches, and that core is locked away for good. The star sheds its outer material, yes, but the heart of it stays behind as a compact remnant. A white dwarf, or a neutron star, or a black hole, depending on how heavy the star was to begin with. Whatever ends up sealed inside that remnant is taken out of circulation. It will never be gas again. It will never form another star. Think of it like water moving through a house. Rain fills the tank, you use the water, it drains away, it evaporates, it falls again as rain. The cycle turns. But imagine that every time the water passes through, a small amount gets sealed into the walls, absorbed somewhere it can never come out. Nothing dramatic happens on any single pass. The tap still runs. but the amount of water free to move through the house is dropping slowly every single cycle, and no rain can ever bring back what the walls have taken. That is what each generation of stars does to the galaxy's supply of gas. Star by star, death by death, a little more matter gets locked into remnants that give nothing back. And the gas that does return comes back changed, enriched with the heavier elements the star cooked in its core, but also diminished. A little less of it free to make the next round than there was before. Every turn of the wheel leaves the wheel a little lighter. The leak has a sharper edge to it, one that reaches back to something we already found. The stars that dominate the universe are the small ones, the red dwarfs, and small stars are the stingiest of all when it comes to giving back. A red dwarf burns for so long and holds itself together so tightly that when it finally ends, far in the future, it simply cools into a remnant and keeps nearly everything. It returns almost no gas to the galaxy at all. The most common stars, the ones the future belongs to, are precisely the ones that take their material and keep it. So, the recycling does not just slow down because gas is running short. It slows down because the kind of star being made is the kind that refuses to recycle. Each generation is more heavily weighted toward these small, hoarding stars, and each generation, therefore, locks away a larger share of what it is given. The cycle is not only leaking, the leak is widening as the universe ages. It helps to put a number on how much gets kept because the fraction is larger than you might guess. Take a star much like our own sun. When it dies, it will puff away its outer layers and leave behind a white dwarf. And that white dwarf will carry something close to half the mass the star was born with. Half of everything the sun is made of will be sealed into a dense ember and taken out of the cycle for good. The other half drifts back to the clouds, free to try again. One star, and half its substance retired permanently on the very first death. You might wonder why the core cannot simply be broken back open. Other things in nature that seem permanent do come apart eventually, given enough heat or force. A white dwarf resists in a way ordinary matter does not. It is held up not by heat, which it slowly loses, but by a stubborn rule about how tightly the electrons inside it can be packed, a rule that does not weaken as the ember cools. So it can sit at the bottom of its own gravity, cold and inert, and still refuse to collapse or scatter. Nothing short of another whole star crashing into it will disturb what it holds. And out in the thinning galaxy of the far future, such collisions grow vanishingly rare. The vault is not merely closed. It is built to stay closed long after the hand that shut it is gone. And that is one of the more generous cases. The sun is a middling star, and it gives back a fair portion. The small stars keep far more. The trend, averaged across all the stars a galaxy makes, runs only one way, toward keeping more and returning less as time goes on. There is no mechanism anywhere in the universe that pries open a white dwarf and hands its material back. Once sealed, sealed. Follow that forward and picture what it means for the far future. Picture the galaxy's gas as an inheritance passed down through a family, generation to generation. Each generation lives on it, and each one, before it goes, buries a portion in the ground where no one after can dig it up. For a long while there is plenty, and no one worries. But the buried portion only grows, and the portion still in hand only shrinks, and no year ever comes in which the ground gives anything back. Run that forward far enough, and the outcome is not in doubt. One day the family is rich only in what it has buried, and poor in everything it can still spend. The galaxy reaches that state too. More and more of its matter ends up frozen inside dead remnants, and less remains as gas that can still catch fire. The dark, locked-away portion swells across the eons while the living, star-making portion dwindles toward nothing. The lights do not go out because the universe grows cold from outside. They go out because the fuel keeps being carried, load by load, into vaults that never open. There is a strange comfort in seeing it laid out plainly, at least for me. The end of the stars is often told as though something goes wrong, as though the universe suffers some failure and winds down in defeat. But nothing here is broken. Every step follows from the simplest facts about how stars live and die, facts we can watch playing out in the sky tonight. The gas is spent because stars are generous with their light, and the vaults fill because stars hold themselves together against their own gravity. The long darkening is not a malfunction. It is the same physics that lit the first stars, carried faithfully all the way to its end. Something almost tender lives in the shape of it if you let yourself feel it. Every star that has ever died did so partly to make the next one possible, giving back what it could. But every one of them also kept a little, held something back at the center that could never be shared. That small kept core is the price of every stellar life, and it is the reason the cycle, for all its patience, cannot turn forever. So, the story of the last star is not really a story about the last star running out of fuel. It is a story about a whole universe slowly moving its matter from one form into another, from bright gas that can burn into dark remnants that cannot, one death at a time, across spans of time that dwarf everything we have met so far. We have talked about these remnants from the outside, as vaults, as sealed cores. But what are they, really? What is left when a star like ours finishes, cools, and settles into that dense little ember it can never spend? To understand the end of all stars, we should look closely at the death of the one we know best. We have been circling the death of stars in general, so let's bring it home to the one star that matters most to us. Our own. The sun feels permanent in the way that only something older than every human memory can. It rose before anyone was here to see it, and it will rise long after. But it is a star like the others, bound by the same rules, and it too has an ending already written into it. The first surprise is when that ending begins. We tend to imagine the sun running steadily for billions of years and then, at some final moment, guttering out like a candle. That is not how it goes. The sun is slowly getting brighter, right now, and has been for its entire life. Every billion years it grows a little more luminous, pouring out a little more heat than it did before. The change is far too gradual to notice across a human lifetime or across all of recorded history, but stretched over the ages it is relentless. It is a fair thing to wonder about why a star would brighten while it is using up its fuel rather than dimming. You would think spending fuel means fading. The answer hides in the core. As the sun fuses hydrogen into helium, the helium ash gathers at the center and packs it more tightly, and a tighter core is a hotter core. A hotter core fuses faster and pushes out more energy, so the sun shines a little more brightly with every passing age. The sun is not brightening in spite of burning its fuel. It brightens because of it, its own spent ash slowly turning up the flame. And that slow brightening, not the sun's eventual death, is what ends life on Earth. This is the detail that catches people off guard. The Earth does not get to wait around for the sun to die. Long before the sun runs low on fuel, its rising warmth will have made our planet unlivable. As the sun grows brighter, the Earth grows hotter, more water evaporates into the air, and that added vapor traps still more heat, driving still more evaporation. Somewhere along that path, the oceans begin to boil away, and once they go, the Earth cannot recover. What makes it final is that the water does not simply move somewhere else. High in the atmosphere, sunlight breaks the water vapor apart, and the light hydrogen freed in the process drifts off into space and is lost for good. A world can survive losing its oceans to the sky and getting them back as rain. It cannot survive losing the water itself, molecule by molecule, off the top of its air. The Earth would not just dry out. It would be quietly emptied of the very substance that made it a living world. The timing here reshuffles the whole picture. The sun has something like 5 billion years left before it truly begins to die. But the oceans may be gone in roughly 1 billion. The surface of the Earth could become too hot for life a full 4 billion years before the sun itself reaches its end. When we picture the sun's death as the thing that finishes us, we have the order wrong. The sun outlives its own living world by an immense stretch of time, carrying on bright and steady above a scorched and empty planet. Set that beside a human span for a moment. 1 billion years is so long that it flattens all of history into nothing. Every civilization, every language, the whole distance from the first stone tool to this very night fits into the last eye blink of it. If life on Earth has that billion years ahead, it is an ocean of time. And yet, against the sun's remaining life, it is only the first fifth of the story. But let's follow the sun itself all the way down, past the loss of the Earth, to its real ending. After billions more years, the hydrogen in the sun's core finally runs low. The core, no longer pushing outward as hard, begins to contract under its own weight. And as it contracts, it heats up. This is the turn that surprises people. A star running out of fuel does not cool down and shrink. It does the opposite. The squeezed core grows hotter than ever, and that fierce new heat pushes the sun's outer layers outward in a vast swelling. The sun becomes a red giant. It bloats outward until it is many times its present size, its surface cooling to a deep red, even as its core blazes hotter than before. Swollen and luminous, it will reach out toward the inner planets, swallowing Mercury, almost certainly Venus, and scorching whatever is left of the Earth to a bare cinder. The gentle yellow star we know will have become something enormous and red, its light falling on a solar system it is half consumed. This red giant phase feels like the climax, but it is really the beginning of the end rather than the end itself. The swollen sun is unstable, and it cannot hold that bloated form for long. Its outer layers, only loosely bound now, begin to drift away into space, lifted off in slow waves until the whole outer envelope of the star has been shed. What had been the body of the sun spreads outward as a glowing shell of gas, thin and expanding, drifting back toward the space between the stars. And here, gently, we meet again the idea from before. Those departing layers are the sun giving itself back, the returned portion of the cycle. That gas, enriched with elements the sun forged over its lifetime, will drift outward and mingle with the clouds of the galaxy, free, in principle, to help form other stars in ages to come. The sun's death is not only an ending, it is a slow exhalation of material back into the place it was born. But not all of it leaves. At the center, where the core once burned, something remains. The outer layers drift away, but the core does not. It stays behind, exposed now, a dense ball of carbon and oxygen about half the mass the sun began with, packed into a sphere no larger than the Earth. This is the white dwarf, the sealed vault we spoke of, the part of the sun that will never return to the cycle. Picture that for a moment. Take something close to half of everything the sun is, the material of a whole star, and squeeze it down until it fits inside a globe the size of our small planet. The density is almost beyond imagining. A single spoonful of white dwarf material would weigh as much as a truck. The sun, having spent its long life spread wide and shining, ends as a tiny, heavy ember, smaller than the Earth it once warmed. There is a quiet symmetry in that, if you look for it. The sun spends billions of years growing, swelling, reaching outward to fill the sky of every world around it, and then draws all of that back down into a point smaller than where it began. The whole grand life of a star, its light, its warmth, the worlds it made possible, ends folded into a sphere you could lose against the face of the Earth. The sun will not explode. It is not massive enough for that. The grand supernovae that scatter stars across the sky are reserved for far heavier stars whose cores collapse in a single catastrophic instant. The sun is too gentle for such a death. It will swell and shed and settle, ending in a long, quiet cooling rather than any blast. No explosion, no shockwave, just a fading ember left where a star used to be. We have followed the sun to its final form, a white dwarf, cooling slowly in the dark. It is easy to assume that from here nothing else happens, that the ember simply loses its warmth over the ages, and that is that. But something remarkable is waiting inside a cooling white dwarf, something no one expected until they looked closely. The corpse of a star does not simply fade. For a while, it begins to change. For a long time, the story of a white dwarf seemed simple. A star dies, leaves behind a hot, dense core, and that core sits there and cools, like an iron pulled from the fire, glowing bright at first, then dimming through orange and red, and finally, to dark. An ember losing its heat to the night. Nothing more to it. That picture is not wrong exactly, but it leaves out the most surprising thing a dying star ever does. Somewhere along the way down, as a white dwarf cools, it begins to freeze. Not freeze the way water does, into ice. Something stranger. The material inside it, the carbon and oxygen left from the star's life, starts to arrange itself into an ordered pattern, locking into place like the atoms in a crystal. The core of the dead star turns, slowly, from a liquid into a solid, into something you could reasonably call a crystal the size of a planet. It sounds almost too poetic to be real, and the first time you hear it there is a temptation to wave it off as a nice image. But it is a plain piece of physics, and it comes from asking a simple question. What happens to matter when you cool it down while it is squeezed as hard as the inside of a white dwarf? On Earth, we know that most things freeze if you make them cold enough. The atoms slow down, lose the energy to slide freely past one another, and settle into a repeating grid. That is what a solid is, at bottom. Atoms that have stopped wandering and taken up fixed positions. Inside a white dwarf, the same thing happens, only under conditions no kitchen freezer could dream of. The carbon and oxygen nuclei are packed unimaginably close, jostling in a hot, dense sea. While the star is still warm, they move too vigorously to hold any arrangement, drifting past each other in a churning liquid state. But a white dwarf has no fresh source of heat. It is a corpse, and corpses cool. As the centuries and the ages pass, the nuclei slow, and at a certain point, they no longer have the energy to wander. They lock together into a vast, ordered lattice, and the heart of the star becomes solid. A lovely difficulty hides in all of this, the kind that makes the science feel alive. How could anyone possibly check such a claim? The freezing of a white dwarf takes billions of years, far longer than anyone could ever watch. You cannot sit beside a dying star with a stopwatch and wait for it to crystallize. The process is slower than the age of the Earth many times over. And yet we have found the fingerprints of it in the sky, which is a small triumph in its own right. The clue lies in how the freezing changes the pace of cooling. When a liquid turns solid, it releases a little burst of heat, the same warmth it once absorbed to melt. Water gives off heat as it turns to ice, though we rarely notice. The freezing white dwarf does the same, on a colossal scale. As its core crystallizes, it releases stored heat, and that fresh warmth slows the star's cooling for a time. The dying ember, right at the moment it should be fading fastest, gets a reprieve, lingering at a certain brightness far longer than it otherwise would. And that lingering is something we can look for directly. If white dwarfs pause in their cooling at a particular stage, then out in the galaxy there should be an unusual number of them gathered at just that brightness, piled up like travelers delayed at a single station along a road. Count enough white dwarfs, sort them by brightness, and if the crystallization story is true, a pileup should appear exactly where the freezing releases its heat. For a long while, this was only a prediction, first worked out in the 1960s by a physicist who followed the logic to its conclusion and said, in effect, the cores of these dead stars should be crystallizing. It was elegant, and it was patient, and it waited half a century for the evidence to catch up. Then a spacecraft mapped the precise brightnesses and distances of a great many nearby stars, far more and far more accurately than had ever been possible. And there, in the data, was the pileup. A crowd of white dwarfs lingering at exactly the brightness where the freezing was expected to slow them. The prediction had come true. Some of the white dwarfs near us, dead stars sitting quietly within a few hundred light years, have solid crystalline cores right now, tonight. The delay the freezing adds to their cooling can stretch to something like 1 billion years. 1 billion years of extra dim glow bought by the heat of the core turning solid. These are not hypothetical objects in a distant scenario. They are real stars, close by, already partway through becoming crystals. What moves me about this is not the crystal itself so much as how we came to know it. No one will ever see a white dwarf freeze from start to finish. The event is too slow for any observer who has ever lived or ever will. And yet we can hold, in hand, the proof that it happens, gathered from a faint crowding in a chart of starlight. We took a process no one can watch, reasoned out the trace it would leave across millions of stars, and then went and found that trace waiting for us. The freezing was always happening, quietly, in the dark above us. We simply learned where to look for the shadow it casts. More is happening inside than freezing alone, and it deepens the strangeness. The core is a mix of carbon and oxygen is the heavier of the two. As the material crystallizes, the heavier oxygen tends to settle toward the center while the lighter carbon rises, a slow sorting by weight, the dense sinking and the light floating over spans of time that make continents seem quick. That settling releases still more energy, gravity itself giving up a little warmth as the star sorts its own insides. It is a small effect next to the freezing, but it points the same way, toward a corpse that keeps finding new ways to shed heat and hold off the dark a little longer. The dead star is not simply sitting still. It is quietly organizing itself, layer by layer, atom by atom, in a slow labor that no one lit and no one tends. Let that image settle without rushing past it. The sun, or a star like it, spends its whole brilliant life as a churning ball of gas, formless, roiling, holding no fixed shape at all. And then, in death, it does something it could never do in life. It becomes ordered. It settles into a structure, a single vast crystal, the most orderly arrangement matter can take. A star spends billions of years in restless motion, and only when it dies does it finally hold still, and in holding still, become a jewel. There is a temptation to make too much of that, so let's stay honest about it. This crystal is nothing like a diamond you could hold, however often the comparison gets made. It is a lattice of bare nuclei under crushing pressure, held in a state that would destroy any ordinary matter instantly. You could not cut it or set it in a ring. But the underlying fact is real, not a flourish. The dead cores of stars do crystallize, do turn solid and ordered, and the sky carries the quiet proof of it. So the white dwarf is not the simple fading ember we started with. It cools, yes, but along the way, it freezes, it sorts itself, it lingers, it becomes a crystal. And still, in the end, all of this only delays the inevitable dimming. The crystal keeps cooling. The glow keeps fading. Given enough time, even this jewel of a star must go dark. Which turns our attention back to the last stars of all. We have watched how a star like the sun dies and crystallizes. But the sun is not the star that ends the universe's long day of light. That honor belongs to the small red dwarfs, and their dying is stranger still, because when the very last of them comes to its end, it will not fade to red at all. We have watched the sun die, swelling into red and then settling into a cooling crystal. It would be natural to assume the last stars go the same way, only later. A red dwarf runs low on fuel, bloats into a red giant, sheds its layers, and fades. The same story, pushed trillions of years into the future. But that is not what happens. The smallest stars die by a different road entirely, and the difference reaches all the way back to how they are built. Remember what made the red dwarf special in the first place. It stirs itself all the way through, the whole star churning slowly from surface to core. That constant mixing is what let it burn nearly all its fuel and live so unimaginably long. But that same mixing changes the ending too. The way a star dies depends on how its fuel is arranged when the end comes, and a red dwarf arranges its fuel in a way the sun never could. The sun, you will recall, burns only in its core and leaves the outer hydrogen untouched. When the core fills with helium ash and the burning falters, that ash sits at the center as a dead weight, and the star responds by swelling into a giant. The red giant phase is really the star's reaction to a clogged, spent core with fresh fuel still trapped uselessly above it. The swelling comes from that mismatch, that separation between where the fuel is and where the burning can happen. A red dwarf never lets that mismatch build. Because it mixes constantly, it never develops a dead core sitting beneath a shell of unused fuel. The helium ash does not pile up in one place, and the hydrogen does not sit stranded out of reach. Everything stays blended, burning evenly, right up until the fuel across the whole star grows truly scarce. And a star that never builds that internal mismatch has no reason to swell. So it does not. The red dwarf will never become a red giant. This is one of those places where following the logic patiently leads somewhere the imagination would not have guessed. If the star does not swell, what does it do as it finally runs down? The answer is the opposite of swelling. As the last of its hydrogen is consumed, the red dwarf contracts, pulling inward under its own gravity with nothing left to push back. And here is the surprising turn. Squeezing a star makes it hotter. As the little star contracts, its surface grows warmer, and its color begins to shift. It moves away from red. A cool star glows red, the way the low embers of a fire do. Warm it, and the color climbs, from red toward orange, toward yellow, toward white, and finally toward blue, the way a poker left in the flames glows from dull red up to searing blue-white as it heats. The dying red dwarf climbs that same ladder of color. Having spent trillions of years as a dim red ember, it grows hotter as it shrinks, brightening and bluing in its final age. The reddest, faintest stars in all the universe end their lives as blue ones. It helps to see why heat and color travel together, since it is the same rule everywhere. Anything warm gives off light, and the hotter it is, the more its glow shifts toward the blue end. A candle flame is cooler at its red edges and hotter in its blue heart. The same holds for stars, and for the coil of a stove, and for iron in a forge. Color is a thermometer you can read with your eyes. So when the dying red dwarf shifts from red toward blue, it is not putting on a disguise. It is simply telling us, in the plainest language light has, that it has grown hotter than it has ever been. There is a name for what they become. Blue dwarfs. And this is the part that never fails to catch me. Not a single blue dwarf exists anywhere in the universe today. Not one has ever existed. The universe is far too young. A red dwarf must burn for many trillions of years before it reaches this stage, and the oldest red dwarfs have used only a sliver of their fuel. Every blue dwarf that will ever be still lies in the deep future, waiting in a time the cosmos has not come close to reaching. So when we speak of blue dwarfs, we are describing stars that are, in the fullest sense, purely predicted. No telescope has seen one. No telescope ever could, not for trillions of years. It is a peculiar thing to describe an object in such detail, its color, its heat, the shape of its death, and know that no eye will confirm a word of it until long after the last human question has been forgotten. We are, in a way, sending a description forward into a future we will never touch, trusting that the physics we can test today will still be keeping its promises then. They exist so far only in the careful working out of what the physics demands, the same patient calculation that told us how long a red dwarf lives and how it burns. Run that physics forward past the end of every star we can see tonight, and it produces these small, hot, blue points, the final generation of stars, lighting up as they die. The calculations even tell us roughly how hot they get. The little star that ends up bluest starts out at around 1/7 the mass of the Sun, and in its dying phase, its surface may climb to something like 8,000 or 9,000 degrees, hotter than the surface of the Sun shines today. Picture that against where it started. A star that spent almost its entire existence as the dimmest, coolest kind of ember in the sky, too faint to see across any real distance, flares at the very end into something hotter and bluer than our own Sun. And then, like the Sun before it, it lets go. The blue phase does not last. Once the hydrogen is truly gone, there is nothing left to burn, and no fuel the little star can reach for. It is far too light to force its core hot enough to burn anything heavier. So the blue glow fades, the star contracts a final time, and it settles into a white dwarf of its own, a small, dense ember left to cool in the dark. But notice what it does not do on the way out. When the Sun dies, it sheds its outer layers and gives a great cloud of gas back to the galaxy. The blue dwarf gives back almost nothing. Having burned nearly all its fuel and swelled at no point in its life, it has no loose outer envelope to cast off. It simply shrinks down and goes dark, keeping virtually all of itself. No glowing shell, no returned gas, no seed for a future star. The last stars die quietly, and they die keeping everything. A stark honesty lives in that image if you stay with it a moment. The very first stars died in brilliant explosions, flinging their substance across space to make everything that came after, planets and oceans and us. The very last stars will do the reverse. They will die without a sound and without a gift, folding their material inward and closing the door behind them. The universe begins its stellar life in generous violence and ends it in silent thrift. So we have reached, in a sense, the moment the whole journey was named for. The last star, a blue dwarf, flares hot and bright for a final age, then contracts and cools into a dark remnant. After it, no star is burning anywhere. The long day of starlight, which began a few 100 million years after the beginning, is over. The sky holds no living stars at all. And yet the story does not end with the last star. That is the strange thing waiting ahead of us. You might think that with the final star gone dark, there would be nothing left to speak of, only cold remnants drifting in the black. But the universe is not finished. Even in a sky with no stars, things still happen, and to see them, we first have to ask what such a sky would even look like. Let's stand, for a while, under a sky in that far era, long before the final blue dwarf, but long after our own age. Say 100 billion years from now, or 1,000. Star formation has all but stopped. The bright stars are long gone, and what remains is a scattering of dim red embers and the dark hulks of dead stars. Step outside, on some world that might still exist, and look up. What would you see? The honest answer is that you would see almost nothing at all. A sky nearly empty of stars. And getting there requires walking through a few changes that will reshape the heavens well before the last light goes out. The emptiness arrives in stages, and each stage is its own quiet event. The first change is close to home, and it is already on its way. Our galaxy is not alone. The great spiral of Andromeda hangs a couple of million light-years off, drifting toward us. And in a few billion years, the two galaxies will meet and begin to merge. It will not be a collision of crashing stars, the distances between stars being far too vast for that. It will be a slow gravitational embrace, the two spirals swinging around each other, tearing and stretching, and finally settling over a long age into a single great ball of stars. That merged galaxy has even earned a name in advance, a blend of the two that made it. And living inside it, the familiar band of the Milky Way across our night sky, that soft river of light, would be gone. The orderly spiral we belong to will have been stirred into a rounder, dimmer, more shapeless swarm. The night sky our descendants might see, if any exist, would already be a stranger place than the one above us now. But the merging of galaxies is not what empties the sky. The deeper change is happening on a far larger scale, and it reaches back to something we touched near the beginning. The universe is expanding, and not merely expanding but expanding faster over time, every distant galaxy drifting away from us and picking up speed as it goes. The more distant a galaxy is, the faster it recedes, and beyond a certain distance, galaxies are carried away so quickly that their light can never again reach us. Follow that forward, and something sobering happens to the sky. One by one, over enormous spans of time, the galaxies beyond our own local group will slip past that threshold and disappear from view. Their light, already stretched and dimmed by the expansion, will fade and redden and finally wink out. Those galaxies have not died. The space between us has simply grown too fast for their light to cross. The observable universe, so full of galaxies today, will empty out from the outside in. A strange loneliness folds into that, and it is better met head-on than glossed over. A distant future astronomer, on some world in that merged galaxy, would look out and see only their own island of stars, with darkness in every direction beyond it. The billions of other galaxies would be gone, not destroyed but unreachable, their light forever lost behind the horizon of the expansion. Such an astronomer might conclude, quite reasonably and quite wrongly, that their galaxy was the whole of everything. The evidence of a wider universe would simply have been carried out of sight. That thought unsettles me more than the emptiness itself. We tend to trust that a careful observer, given enough time and good instruments, can always work out the truth of things. But this is a truth that simply expires. The expansion does not hide the other galaxies behind dust or distance we might one day see through. It removes them from the reach of any possible measurement, forever. A future astronomer could be brilliant, patient, and completely honest, and still be certain of a picture of the cosmos that is fundamentally incomplete, with no way, even in principle, to know what was missing. The universe does not only end its stars. Along the way, it quietly closes off the chance to understand what it once was. We happen to live at a time when that evidence is still here. The distant galaxies are still visible, the expansion still readable in their light. Far in the future, none of that will be recoverable. The knowledge we have gathered about the universe's size and history depends on light that is, in the long run, on its way out the door. There is something quietly moving in that, in being alive during the window when the universe still shows its own past. So the far sky empties of galaxies. But what of the near sky, the stars of our own merged galaxy? Here the emptying is slower but just as sure. The bright stars burn out first and are not replaced, since new star formation has faded to almost nothing. What remains are the red dwarfs, the long-lived embers, growing fewer as the ages pass. And red dwarfs are so dim that even nearby they are hard to see, and across any real distance they are invisible to the eye. So the night sky of that era would hold only a sparse handful of faint red points, if that. Gone the brilliant blue and white stars. Gone the crowded band of the Milky Way. Gone the other galaxies entirely. A being standing on a planet then, looking up, would see a darkness broken by only a few dull red sparks, and beyond them, nothing. The rich sky we take for granted, thick with stars on a clear night, is a feature of this early, crowded age, not a permanent fixture of the universe. It is a fair thing to ask what such a world would even be like, one of these planets circling a late red dwarf. The nearest red dwarf to us today gives a small preview. It is a feeble star, putting out something like a 7/100th of the sun's light, so dim that a planet would have to huddle very close to stay warm enough for liquid water. Close enough that the planet would circle its star in a matter of days rather than a year. A whole orbit, a whole year, over almost before it began. And a world that close to its star tends to become locked, one face held permanently toward the star, the other turned forever to the dark. One side in endless dim red daylight, the other in unbroken night. There would be no sunrises and no sunsets, only a single fixed red glow hanging always in the same spot in the sky, or never appearing at all, depending on where you stood. I find it hard not to pause on how different such a life would be if life could take hold there. No bright blue days, no scattered stars overhead, no sense of a wider sky full of other suns. Just a dim red star fixed in place, a sky otherwise nearly black, and the deep quiet of a universe that has spent most of its light. Whatever might live there would have no reason to imagine the crowded, brilliant cosmos we were born into. To them, this thinned and reddened sky would simply be how things are. But even that dim red world, even that sparse sky, still counts as a lit universe. There are still stars, however few, however faint. The long day is not over yet. These late red dwarfs will burn on for trillions of years more, outlasting everything, until the very last of them flares blue and dies. And when it does, the sky finally holds no stars at all. So we are led, gently, to the real question underneath all of this. The question is no longer what a nearly dark sky looks like, but what happens after the darkness is complete. Once the last star is gone, the universe is not empty of energy, not yet. And wherever there is energy, there is the faint possibility of something using it. Which is where a remarkable idea enters, one that asks whether anything at all could go on living in a universe with no stars left to warm it. Most people never think to ask what life runs on, because the answer seems too plain to bother with. Heat, surely. The easy answer is heat, or warmth, or energy. A cold universe sounds like a dead one, and a warm one alive. But that easy answer is not quite right, and getting it right opens a door that most people assume is bolted shut. Life does not run on heat. It runs on a difference in heat, a flow from something warmer to something cooler. Your body does not stay alive because it is warm. It stays alive because it is warmer than the air around it, and energy keeps moving from you outward into that cooler surrounding. Every meal you eat, every breath, feeds that flow. A living thing is a place where energy is passing through, from a warm source to a cool sink, doing a little useful work on its way by. Picture a water wheel in a stream. The wheel does not turn because the water is high. It turns because the water falls, moving from a high place to a low one, and the wheel takes a little work from that fall. Raise the whole stream, lake and all, 10 feet higher, and if the water no longer falls, the wheel does not turn at all, however high it sits. What matters is not the level but the drop. Life is a wheel in the stream of energy, turning on the drop from hot to cold. This shifts the whole question of the far future. The worry was that a cold universe cannot support life. But coldness alone is not the problem. As long as there is any difference in temperature anywhere, any warm spot beside a cooler one, there is a drop for the wheel to turn on, and in principle, something could live on it. The universe does not need to stay warm. It only needs to keep some unevenness, some gradient, however faint. This is the door that a physicist named Freeman Dyson pushed open back in the 1970s. He asked a question that sounds almost innocent. If the universe goes on expanding and cooling forever, must life necessarily end? Everyone assumed the answer was yes, that the long cold was the end of any possible living thing. Dyson was not so sure, and he worked the problem through with real care. His reasoning went like this. Suppose you are some form of life in that cold future, running on a tiny remaining difference in temperature. The universe keeps cooling, so that difference keeps shrinking, and the energy you have to work with grows ever more scarce. It sounds hopeless, but Dyson noticed something about the cost of living. The colder your surroundings, the less energy each thought, each act costs you. In a colder world, the same flicker of thinking can be done for less. This is the part that feels like a trick until you look closely, and then it feels like a gift. Any act of thinking, anything that sorts or decides or remembers, has to dump a little waste heat into its surroundings, the way a working engine warms the air near it. How much energy that costs turns on how warm the surroundings already are. Dumping heat into a hot room is expensive, since you have to push against all that existing warmth. Dumping the same heat into a near-frozen void costs almost nothing, because the cold is so eager to receive it. So as the universe grows colder, the price of a single thought drops right along with it. And a being clever enough to wait can buy its thinking at a discount that keeps deepening. So, a being in that future has a strategy available. As the universe cools, it can slow itself down to match. It can think more slowly, act more slowly, lower its own inner temperature to stay just above its surroundings. And because everything is colder, each of those slow thoughts costs almost nothing. It stretches its life without finding a scrap more edges out, needing less and less for each moment of experience instead. And Dyson added one more move, the one that makes the whole thing work. Rest. The being does not run continuously. It thinks for a while, then goes dormant, radiating away its waste heat during the sleep, cooling back down before it thinks again. Active spells, then long hibernations, then active spells once more. By spending most of its existence asleep, it lets the universe cool further between thoughts, so each waking spell is cheaper than the last. A homely version of this we already half understand. A person rationing a small amount of food across a long winter does not eat less at every meal and slowly starve. They eat, then rest, then eat again, spacing things out so the store lasts. Dyson's creature does the same with energy and with time itself, only carried to an extreme no living thing on Earth has ever needed. It spaces its very thoughts across widening gulfs of years, then centuries, then spans with no familiar name, resting through each gap so the little it has will never quite run dry. When Dyson followed the arithmetic of this, he found something startling. A being that keeps slowing down and resting this way could, in principle, think an infinite number of thoughts on a finite store of energy. It would not merely live for a finite time. It would live for all of time. An unending stream of experience, stretched thinner and thinner but never stopping, paid for by a fixed and finite budget of energy. Immortality, of a strange and patient kind, purchased through slowness rather than abundance. Let that sink in for a moment, how quietly radical it is. The picture we had was of a universe that runs down and takes everything living with it. Dyson offered a different picture. Life need not race the cooling and lose. It could ride the cooling, slowing in step with it, thinking its endless slow thoughts across spans of time that dwarf the entire age of stars. A mind that experiences as much in the deep cold future as we do now, only spread across eternities between one thought and the next. There is something almost tender in the vision, and it is easy to see why it moved people. It suggests that meaning, experience, thought itself, might not be a brief accident lit by stars and snuffed out when they fade. It might be able to continue in some form into the deepest dark, carried by nothing more than a faint and fading difference in temperature. The last warmth of the universe, tended carefully, might never quite run out of things to think. Part of what draws me to the idea is how gentle it is. It does not ask the future to be grand, or crowded, or bright. It asks only for patience, and for a willingness to live slowly, and it finds in those humble things a kind of forever. Whatever you make of whether it could ever be true, it is a strangely kind thought to carry into the dark. Dyson knew he was reaching, and he said so plainly. He was not claiming this would happen, only that the laws of physics, as understood at the time, did not forbid it. The cold future did not have to be empty. There was, at least on paper, a way through. For a while, this was one of the most hopeful ideas in all of cosmology, a real escape hatch written in the language of thermodynamics. But notice the quiet condition tucked inside the whole argument. Everything depends on the universe cooling gently and steadily, forever, leaving always some small difference in temperature to work with. Dyson built his eternity on the assumption that the cold would keep deepening smoothly, without limit, so that a patient enough being could always find a slightly cooler place to shed its heat into. And that is exactly the assumption that would soon come into question. Because in the years after Dyson wrote, we learned something new about how the universe expands, something he could not have known when he first worked it all out. The discovery would arrive from an unexpected direction, and it would ask a hard question of Dyson's beautiful escape. To see why, we have to look at what happens to a universe that does not simply cool, but is pulled apart faster and faster as it goes. Dyson's escape rested on one gentle assumption: that the universe could keep cooling forever, always leaving somewhere a little colder to shed heat into. Take that away, and the whole patient path to eternity closes. And the universe may not let it stay open. There may be a temperature below which the cosmos simply cannot go, a floor beneath the cold. To see where such a floor comes from, we have to return to the expansion and to the odd fact that it is speeding up. For most of the 20th century, the expectation was that the universe's expansion would gradually slow, dragged on by the gravity of everything within it. Then, near the end of the 1990s, careful measurements of distant exploding stars showed the opposite. The expansion is accelerating. Something is pushing space apart, and pushing harder as time goes on. We call that something dark energy, a name that politely covers how little we understand it. For our story, the name matters less than the consequence. An accelerating universe behaves very differently from a coasting one, and one of the differences reaches straight into Dyson's dream. When expansion accelerates, every observer becomes surrounded by a kind of horizon, a boundary beyond which things are being carried away too fast for any signal to cross back. It is not a wall you could touch, only a limit on how far you can ever see or reach, fixed by the pace of the expansion itself. We met one face of this horizon already, when the distant galaxies slipped out of view. But the horizon does something stranger than hide galaxies. It glows. A horizon like this is not perfectly cold or perfectly silent. It gives off a faint, steady warmth, a whisper of radiation with a definite temperature, arising from the deep physics of a horizon in an accelerating space. This is a subtle idea, so let's take it slowly. The clearest comparison is to another kind of horizon we will meet again later, the edge of a black hole. A black hole, though nothing should be able to leave it, glows very faintly with a temperature of its own, a discovery that reshaped physics when it came. The horizon of an accelerating universe behaves in a similar way. The mere existence of a boundary that traps information gives that boundary a temperature. And so the whole of space, surrounded by such a horizon, is bathed in an unremovable faint warmth. It is fair to feel that this makes no sense at first. That empty space glowing simply from having an edge sounds like a contradiction. The rough idea is that empty space is never truly still. Down at the smallest scales, it seethes with fleeting activity, pairs of particles flickering into being and vanishing again faster than anything can catch them. Ordinarily, they cancel out and leave nothing behind. But a horizon can interrupt that cancellation, letting one of a pair slip beyond reach while its partner is left behind as real, lasting warmth. The boundary, in effect, keeps skimming a little something from the restless emptiness, and that steady skimming is the warmth that will not switch off. Now hold that beside Dyson's plan and feel the trouble arrive. His whole strategy depended on the universe growing ever colder, so a patient being could always find a cooler place to dump its waste heat. But if the horizon gives off a fixed temperature, then the universe cannot cool below that temperature, ever. It sets a floor. No matter how long you wait, the surrounding warmth will not drop past this level, because it is not left over from the past, like the fading heat of the Big Bang. It is generated fresh and forever by the horizon itself. This is the difference that undoes everything. The warmth of the early universe was an inheritance, spent down over the ages, growing colder as it thinned. A being could count on that kind of warmth to keep fading and plan around it. The horizon's warmth is not an inheritance being spent. It is an income. The universe keeps paying itself at the same rate, with no end and no decline. You cannot outwait an income. However long you rest, it is still there when you wake, exactly as warm as before. Think about what a floor does to the water wheel. Life ran on the drop from warm to cold, the wheel turning as energy fell from a high place to a low one. A floor beneath the cold means the low place can only get so low. Once your surroundings reach that floor temperature, you can no longer shed heat into them, because they are just as warm as the coldest thing you can make. The water has reached the bottom of the valley. There is nowhere lower for it to fall, and the wheel, at last, must stop. That is the quiet blow to Dyson's eternity. A being trying to think forever needs somewhere to send its waste heat, and the floor takes that away. Once the universe settles at its minimum temperature, a mind can no longer cool itself between thoughts, no longer find the drop it needs to keep turning. It is not that the being runs out of energy in the ordinary sense. It is that the universe stops offering any colder place to pour energy into. And without that, thought itself has no room left to happen. It helps to put a number on this floor, faint as it is. The temperature the horizon settles to is almost inconceivably cold, something like 100 billion billionth of a degree above absolute zero. A number so small it barely deserves to be called a temperature at all. Compared to it, the coldest empty space we know today is blazing hot. And yet that unimaginably tiny warmth is still not zero, and being not zero is the whole point. It is a floor, however low, and a floor is all it takes to stop the wheel. What strikes me here is how little it takes to change everything. Dyson's eternity did not fail because the universe ran out of energy, or grew violent, or fell apart. It failed, if it fails, over a warmth so faint that no instrument we could ever build would register it as anything but perfect cold. The difference between forever and merely a very long time hangs on a temperature too small to name comfortably. The universe does not need a grand gesture to close a door. A whisper of heat, held steady, is enough. A certain irony sits in where this leaves us, and it is better named plainly than left implied. The very same dark energy that pulls the distant galaxies out of sight, that empties the far sky, also lays down this floor beneath the cold. The force that isolates every observer is the same force that denies them the endless cooling Dyson's plan required. One property of the universe closes two doors at once: the door to the distant stars and the door to thinking forever. We can even see the floor approaching, in a way, in the heat left over from the birth of the universe. That ancient warmth, the afterglow of the Big Bang, still fills all of space, and it has been cooling steadily as the universe expands. Today, it sits at a few degrees above absolute zero. It will keep dropping for a very long time. But it will not drop forever. Far in the future, that cooling afterglow will sink down toward the horizon's tiny temperature, and there it will level off and stop, coming to rest at the floor and going no lower for the rest of time. So the picture Dyson painted, beautiful as it was, seems to run into a wall the universe itself builds. The wall is not exhausted fuel, as we might have pictured. It is temperature, a warmth that will not go away, quietly forbidding the endless cold his eternity was built upon. The escape hatch, on closer inspection, may open onto a floor. And yet a single physicist worked this through in detail and put the argument in a form that could be checked and argued with. It was not enough to say the horizon glows and leave it there. Someone had to take Dyson's own reasoning, insert this floor into it, and see exactly where the dream broke and whether it broke completely or left some narrow way through. That careful reply came about 20 years after Dyson wrote, and it is where we turn next. Around the year 2000, two physicists took Dyson's dream and tested it against everything we had learned since he first wrote it down. Lawrence Krauss and Glenn Starkman went through the argument step by step, hoping to see whether it could still stand in a universe that accelerates rather than merely to knock it down. What they found was that the trouble runs deeper than the floor alone. The floor was one blow, and we have already met it. But there is a second, and it comes from the same horizon. Remember that in an accelerating universe, every observer is wrapped in a boundary beyond which things are swept away for good. That boundary does not only glow, it also fences you in. Everything you could ever reach, every scrap of matter and energy you might ever gather to yourself, lies within that horizon. And its total is fixed. Finite. This is the piece Dyson could not have accounted for, because the acceleration was not yet known in his day. He imagined a being that, over eternity, might slowly gather more and more resources, reaching ever farther for fuel as it needed it. In a coasting universe, that reaching has no fixed limit. But in an accelerating one, the horizon draws a line around your entire future. Whatever lies beyond it is receding faster than you could ever chase, and it grows more unreachable with every passing age, not less. You are sealed inside a finite allowance, with no way to ever add to it. Picture it as a warm house in a spreading winter. Dyson pictured someone who could always walk out and gather more firewood from an endless forest, burning it slowly, resting between fires, lasting forever on wood forever replenished. Krauss and Starkman pointed out that the forest is not endless. The horizon fences off a yard of finite size, with only so many trees inside it, and every tree beyond the fence is drifting away too fast to ever reach. You have exactly the wood in your own yard, and not one stick more, for the rest of time. And the yard itself keeps shrinking, in a sense that makes the trap tighter still. As the expansion carries on, more of what lies near the fence drifts across it and out of reach, so the reachable store does not merely stay fixed. It slowly dwindles as things you had counted on are swept beyond the horizon before you can gather them. A being in that future is not simply rationing a fixed pile of wood. It is rationing a pile that is quietly being carried off at the edges faster than any effort could keep up with. Every delay, every long, restful sleep, meant to save energy, also lets a little more of the world escape while the sleeper waits. Now put the two problems together, the finite fuel and the floor beneath the cold. A finite store of energy might still be stretched a very long way if you could keep finding somewhere colder to work against. That was the whole genius of Dyson's slowing and resting. But the floor forbids it. Once the universe reaches its minimum temperature, the resting no longer helps. because there is no colder place to cool into during the rest. The two limits close on the being together. A fixed budget it can never grow, and a floor it can never get below. Between those two walls, the conclusion is hard to escape. It helps to see why the two limits are so much worse together than apart. A floor with unlimited fuel would still allow a great deal, since you could burn freely even if you could not cool efficiently. Unlimited cooling with finite fuel would allow a great deal too, since Dyson's slowing trick could stretch a small budget across forever. Either limit alone leaves a door ajar. It is only when both clamp down at once, a fixed store of energy and no colder place to spend it, that every door swings shut. A being in an accelerating universe cannot think forever. It can think for an enormous span, longer than we have any words for, but not without end. Sooner or later, the finite energy inside the horizon is spent down to the floor, and no strategy of patience can wring another thought from it. The escape hatch, followed all the way to its end, closes. Krauss and Starkman put it plainly. In a universe like ours, life must eventually cease. It is a lovely and humbling thing to watch how this reversal happened because of what it shows about how science moves. Dyson was not careless. His reasoning was sound for the universe he thought he lived in, a universe coasting along, gradually slowing, cooling without limit. Nothing in his argument was wrong on its own terms. What changed was not the logic but the world underneath it. In 1998, the discovery that the expansion is accelerating quietly pulled the ground out from under the older picture, and an argument that had been a beacon of hope became, in the new universe, an argument with a limit built in. Think about what that means for a moment. No one refuted Dyson by finding a flaw in his equations. The equations were fine. Reality simply proved to be a different kind of place than anyone had assumed, and that single change of setting flipped a hopeful conclusion into a sobering one. The same careful mind, given the true universe, would have reached the sobering answer from the start. He was working with the best picture his time could offer, and the picture moved. I find something quietly moving in that, and not only sad. Dyson lived long enough to see the discovery that undid his hopeful vision, and he took it in stride, the way the best scientists do. To offer an idea into the world knowing it may be overturned by the next measurement, and to mean it as a gift rather than a claim of ownership, is a kind of grace that the work quietly demands. The eternity he sketched was never really a promise. It was a careful question, honestly asked. And a question can be answered no without losing any of its beauty. Something in watching that happen is clarifying rather than dispiriting. It is easy to imagine that a beautiful idea, once proposed by a brilliant person, ought to stand or fall on its own cleverness. But this is not how it works. An idea about the far future is only ever as good as our picture of the universe it lives in, and that picture keeps being corrected by what we measure. Dyson's eternity did not lose to a better argument. It lost to a better measurement, made 20 years after he wrote. And we should be honest that even this is not the final word. The whole reversal rests on dark energy behaving the way it appears to, staying constant, holding that horizon and that floor in place forever. We do not fully understand dark energy. If it were to weaken over time, or change in some way we have not yet measured, the horizon could loosen and the floor could fall, and Dyson's long, slow eternity might quietly become possible again. The door that Krauss and Starkman appeared to close is only as firmly shut as our understanding of the strangest thing in the universe. So, where does this leave the question we started with, whether anything could live on in a universe without stars? The most honest answer, given what we now know, is that it probably cannot, not forever. The cold future looks likely to be, in the end, a lifeless one. But that answer is written in pencil, not ink, resting on a piece of physics we openly admit we do not yet grasp. And notice something about all of this. Every path we have followed, Dyson's hopeful one and the sobering reply, has been about living things, about minds trying to persist. But minds may not be what lasts longest in this universe. Long after the last possible thought has been thought, other things will still be out there, enduring in the dark, changing so slowly that they make the lifetimes of stars look brief. And the most patient of all of them is an object we have mentioned only in passing, one that is not even finished growing yet. Almost everything you have ever heard about black holes says they take. They swallow, they devour, nothing escapes. And so it comes as a real surprise to learn that black holes leak. Very, very slowly. A black hole gives off a faint trickle of radiation and loses a little of itself. And given enough time, an unthinkable amount of time, a black hole can evaporate away entirely. The greatest traps in the universe are, in the end, not permanent. This was one of the most startling results in modern physics when it arrived, worked out by a young researcher puzzling over what happens right at a black hole's edge. The details are deep, but the picture we can hold is this. The edge of a black hole, its horizon, is not a perfectly dead boundary. Like the cosmic horizon we met before, it has a temperature. It glows, ever so faintly, with radiation, and anything that glows is losing energy, and so losing mass, little by little. And this is where it becomes strange, where a lovely piece of backward logic comes in. For almost anything else in the universe, being bigger means being able to hold more heat and being hotter. Black holes do the reverse. The bigger a black hole is, the colder it is. The smaller it is, the hotter it glows. A little black hole is feverish, radiating strongly and shrinking fast. A giant one is colder than almost anything, barely glowing at all, and it takes almost forever to lose even a sliver of its mass. It is fair to want a reason for something so upside down, and there is a rough one to hold. The radiation a black hole gives off comes from its very edge, and the size of that edge is set by the black hole's gravity. A small black hole has a tightly curved edge, sharply bent, and that sharp bending is what makes it glow hot. A giant black hole has an edge so vast and so gently curved that, up close, it would seem nearly flat, and a nearly flat edge barely radiates at all. So the hugeness that makes a black hole seem most fearsome is exactly what makes it coldest and most nearly eternal. Size and stillness go together. Let's put a number on just how cold a real black hole is, because it is hard to believe otherwise. Take a black hole about the mass of the Sun. Its temperature is around 60 billionths of a degree above absolute zero. That is not a figure of speech for very cold. It is colder than the empty space between the stars today, colder than the faint afterglow of the Big Bang that fills the sky by a wide margin. The afterglow sits at a few degrees above absolute zero. The black hole sits at 60 billionths of one. To feel the size of that gap, the black hole is colder than its surroundings by something like 45 million times over. Imagine trying to warm yourself at a fire that is tens of millions of times colder than the winter air around you. The fire would not warm you at all. The air would pour its heat into the fire instead. That is the exact situation a black hole finds itself in today. A thing so cold that even the near-frozen sky is a furnace by comparison. And that gap changes everything about the near future of black holes. A thing colder than its surroundings does not lose heat. It gains it. Set an ice cube in a warm room, and it does not cool the room. The room warms the cube. Heat always flows from warmer to colder. And a black hole today is far colder than the space around it. So a black hole is not evaporating right now. Quite the opposite. It is absorbing more than it gives off, feeding on the faint warmth of the sky and slowly growing. Let that reversal land for a moment, because it turns the whole story around. We tend to think of black holes as slowly dying, dribbling away their mass. Not yet. Not for an almost inconceivable stretch of time. Right now, and for ages to come, every black hole in the universe is still eating. Not from stars or gas, since much of that is gone or beyond reach. It feeds on the thin bath of radiation left over from the beginning. The black holes are gaining weight from the light of the young universe, drinking in the last warmth of the dawn. For a black hole to begin truly evaporating, to start losing more than it gains, the sky around it has to grow colder than the black hole itself. And the sky is cooling as the universe expands and that ancient afterglow thins out. But it has a long, long way to fall. It must drop from a few degrees down past the black hole's 60 billionths of a degree. And only then, when the sky is colder than the hole, does the balance finally tip. The timescale for this is where the mind simply lets go. The afterglow of the Big Bang will not cool below the temperature of a sun-sized black hole until the universe is something like 10 times its present age, just to make a start, and far longer, unimaginably longer, for the truly giant black holes at the centers of galaxies. Only after the sky has cooled beneath them, ages upon ages from now, do black holes cross over from growing to dying, and only then does the slow leak begin to win. It helps to dwell on how patient these objects are, because patience is really their defining trait. The stars live and die in millions or billions of years. The last red dwarfs hold on for trillions. But the black holes outlast all of them by amounts that make trillions look instantaneous. Long after the final star has gone dark, long after any possible living thing has thought its last thought, the black holes will still be there, barely changed, waiting out the cold in near-perfect stillness. A quiet grandeur lives in that, and it rewards a moment's attention. When everything else has ended, when the sky holds no stars and no minds and no warmth to speak of, the universe is not quite empty. It still holds these dark, silent, immensely patient things, each one a scar left where a great star once collapsed, or where a galaxy once fed a monster at its heart. For an era longer than all the eras before it combined, the black holes are what the universe is made of. And they do not last forever either. Once the sky finally cools below them, the leak takes over, and across spans of time with no name, they begin to shrink. As a black hole loses mass, it grows hotter, and as it grows hotter, it radiates faster. So the process, glacial for almost its entire length, speeds up toward the end. The last moments of a black hole, after an eternity of patience, are quick. A final flash, and it is gone, leaving only spreading radiation where it used to be. There is something almost unbearable in the shape of that ending when you set it against the whole life that came before. A black hole can spend a length of time so vast that every earlier era of the universe, all the stars, all the light, all the life, amounts to less than a single tick at the start of it. And then, at the very end, after all that stillness, it finishes in what is, by comparison, an instant. An eternity of patience, closed by a brief flare. The most enduring thing the universe ever built goes out not with a long fade, but with a sudden final flash, as if the waiting had all along been the point, and the ending merely the release of it. So even the most enduring things the universe can make have an ending written into them. Slower than stars, slower than minds, slower than almost any process we can name, but an ending all the same. The black holes are the universe's last great structures, and they too are on the clock. Counting down across numbers so vast, they stop meaning anything at all. But all of this, the growing, the waiting, the slow evaporation, rests on one assumption we have not yet examined. That the matter inside these objects, and inside every cold remnant drifting in the dark, is itself permanent. That a proton, the tiny particle at the heart of every atom, lasts forever. And that is something no one is entirely sure of. If matter itself has a lifetime, then the whole story changes again, and it changes long before the black holes are done. Everything we have built in this story rests on a floor we never thought to check. That matter lasts. That the stuff a dead star is made of, the stuff you are made of, simply endures, sitting there unchanged for however long the universe demands. We have watched stars die and remnants cool and black holes wait out the ages, and all of it assumed that the atoms themselves were permanent. But are they? The question sounds almost strange to ask. Of course matter lasts. A rock left alone stays a rock. Yet when physicists look closely at the particles inside every atom, they find that permanence is not guaranteed at all. It is a hope, a very well-supported hope, but not a certainty. And the particle the whole question turns on is the proton. The proton is one of the building blocks at the center of every atom. Every atom in your body, every atom in every star and planet and drifting cloud of gas is held together around protons. They are, as far as we have ever been able to tell, utterly stable. No one has ever watched a proton fall apart. For all of ordinary experience, a proton is forever. But some of our deepest theories about how nature works whisper otherwise. When physicists try to unify the forces of nature, to fit them together into a single underlying scheme, many of those attempts predict something quietly unsettling. They suggest that the proton is not perfectly stable after all, that once in a very great while, a proton should simply decay, breaking apart into lighter particles and vanishing as the thing it was. Not struck apart, not broken by any outside force, just coming undone, on its own, from within. It is fair to ask why anyone would suspect such a thing of a particle that has never once misbehaved. The suspicion grows out of a hope physicists have long carried, that the forces of nature, which look so different to us, are really one force wearing different masks. In the earliest instance of the universe, when everything was unimaginably hot, those forces may have been united, and only as things cooled did they split into the separate forces we see. The theories that try to describe that lost unity tend to allow the particles inside atoms to shift into one another in ways ordinary physics forbids. And once such shifts are allowed at all, even the proton loses its perfect safety. The very idea that would make nature simpler and more beautiful also, quietly, gives matter an expiration date. If that is true, it does not matter how gently you treat a piece of matter. Lock it away in perfect cold and stillness, protect it from everything, and still, given enough time, its protons would one by one dissolve. The rock would not last. The dead star would not last. The cold remnants drifting in the dark, the crystallized white dwarfs, even the material that would have fed the black holes, all of it would slowly evaporate from the inside, atom by atom, over spans of time that beggar the imagination. How long, though? This is where the numbers become almost comic in their size. If protons decay at all, they do it so rarely that the wait is staggering. We know it must be enormously long, because we have looked, and looking is a story in itself. The way physicists hunt for something that might take forever to happen even once is quietly clever. You cannot watch a single proton and wait, since you would be waiting longer than the age of the universe many times over. But you do not have to. Instead, you gather an enormous number of protons together in one place and watch them all at once. If a single proton would take an unthinkable span to decay, then a vast crowd of them, watched together, should produce a decay here and there on a timescale you can observe within a human career. So, physicists built a detector to do exactly that. Deep underground, shielded from the confusing rain of particles that showers the surface, they placed an immense tank of pure water, tens of thousands of tons of it. Water is full of protons, and this much water holds a staggering number of them. Around the tank they arranged thousands of sensitive eyes, detectors watching in the dark, ready to catch the tiny flash a decaying proton would give off. Then they waited and watched for years. It helps to grasp just how many protons sit in a tank like that, because the number is what makes the patience pay off. A single cup of water already holds more protons than there are stars in the observable universe. Fill a tank with tens of thousands of tons of it, and the count climbs past anything the mind can picture. So even though any one proton might wait longer than the universe has existed to decay, watching so many at once means that, if decay happens at all, a few should give themselves away while patient people are still looking. The vastness of the wait is answered by the vastness of the crowd. And in all that watching, across all those years and all those countless protons, they have seen not a single proton decay. Not one. Now, that silence is not a failure. It is itself a measurement, and a powerful one. Because so many protons were watched for so long with nothing happening, we can say with confidence that if the proton decays at all, its lifetime must be almost unspeakably long, longer than 10,000 trillion times the current age of the universe. That figure is hard to hold, so try it from the other side. If you picked one proton and simply sat with it, you would have to wait through the entire life of the universe so far, then do it again and again, more times than there are grains of sand on every beach on Earth, before you had any real chance of seeing it go. And even that may be far too short. The number is only a lower limit, the point past which our patience so far cannot yet see. Let that settle for a moment, because it cuts two ways. On one hand, it means matter is astonishingly stable, far more stable than everyday life would ever require. A proton, if it dies at all, outlives the current universe by a margin so vast the comparison loses meaning. On the other hand, that experiment has not proven protons are eternal. It has only pushed the possible lifetime further out. The proton might still decay, just even more rarely than we have yet been able to rule out. The door is not closed. This leaves us in a truly uncertain place, and it is better to rest in that honestly than to pretend otherwise. We do not know whether matter is truly permanent. If protons never decay, then the cold remnants and the black holes play out the story we have been telling, enduring until evaporation slowly claims them. But if protons do decay, even at the glacial rarest rate still allowed, then a different ending arrives. One where matter itself quietly dissolves long before the black holes finish their patient wait. I find it strangely stirring that the fate of everything hangs on the behavior of the smallest thing. Whether the last dark remnants of the universe endure for ages or slowly melt into nothing comes down to whether a single tiny particle, the proton, is truly forever or only nearly so. The grandest question about the end of all things comes down to a question about the most ordinary building block of matter. The same particle sitting, right now, in every atom of your hand. And suppose, for the rest of our journey, that protons do endure, that matter holds. Even then, the cold remnants are not as quiet inside as they look. Something is still happening within them, slower than almost anything in nature. A process so faint it makes the drift of continents seem frantic. Deep inside those frozen dead stars, a fire still burns, in the barest, slowest sense of the word, and where it leads is stranger than anywhere we have been. Picture one of these dead stars far in the future, a white dwarf that has long since crystallized and cooled. It sits in the dark, colder than anything we could make, with no fuel burning and no heat flowing. By every ordinary measure, it is finished, inert, a frozen relic. And yet, deep inside it, something is still slowly happening. A process so patient, it makes everything else in this story look hurried. To see what, we have to remember what fusion is, and why stars normally need to be so hot to do it. Fusion is the joining of small atomic nuclei into larger ones, and it is how stars make their light. But nuclei do not want to join. Each one carries a positive charge, and like charges push each other away, hard. To force two nuclei close enough to merge, you normally have to hurl them together with tremendous speed, and that speed is heat. A star's core is millions of degrees, precisely so its nuclei move fast enough to slam past that repulsion and fuse. So in a cold, dead star, with no heat to speak of, fusion should be impossible. The nuclei are barely moving. They cannot possibly charge through the wall of repulsion between them. And by the rules of the everyday world, that would be the end of it. No heat, no speed, no fusion. The dead star should simply sit there, changeless, forever. But the world of the very small does not play by everyday rules. Down at the scale of particles, there is a strange and well-tested phenomenon that lets a particle do something that should be flatly forbidden. It can pass through a barrier it does not have the energy to climb over. It does not leap over the barrier, and it does not smash through. It simply appears on the far side, as if the wall it could never surmount had, once in a great while, quietly let it slip through. Physicists call this tunneling, and it is not a trick or a metaphor. It is a real and measured feature of how nature works at the smallest scales. Think of it like this. Imagine rolling a ball toward a hill it does not have the speed to crest. In the ordinary world, the ball rolls partway up, stops, and rolls back every single time. But if the ball were a particle, then once in an enormous number of tries, without ever having the energy to reach the top, it would simply turn up on the other side of the hill, having crossed through the place it could never have climbed. The smaller the particle and the thinner the hill, the more often this happens. For most everyday things, it essentially never does. For nuclei pressed close together, over long enough spans of time, it does. This is not some fragile idea invented to fill a gap in the story. Tunneling is the reason the sun shines at all. Even in the sun's blazing core, the nuclei are not quite moving fast enough to fuse by brute force alone, and it is this quiet slipping through of the barrier that lets the reactions happen and lights the star. The same effect that warms your face on a summer afternoon is the one that keeps a dead star faintly working in the dark. So even in the cold heart of a dead star, fusion has not truly stopped. It has only slowed to a crawl beyond imagining. They are never thrown together by speed. Given a long enough wait, the barrier between them is simply passed. The dead star is still fusing, just unthinkably, unimaginably slowly. And this slow, cold fusion has a direction. It does not wander aimlessly, building heavier and heavier elements without end. It moves, over vast time, toward one particular destination and then stops, toward iron. There is a deep reason iron is where this road ends, and it is one of the most quietly important facts in all of nature. When light nuclei fuse into heavier ones, they can release energy, which is what powers the stars. But this only works up to a point, and that point is iron. Iron sits at the very bottom of a kind of energy valley. Fusing anything lighter than iron into something closer to iron releases energy and is, in a sense, downhill. Fusing iron into something heavier would cost energy, an uphill climb that will not happen on its own. Iron is the place where matter has given up all the energy it can give. It is the ash at the bottom of every possible fire. It helps to see why any single element should hold this special place, since it is not arbitrary. Think of the particles inside a nucleus as held together by tiny springs, and the tightness of those springs as a kind of comfort. Very light nuclei are loosely held, a little uncomfortable, and they can settle into something snugger by joining together. Very heavy nuclei are strained in the other direction, packed so full that they would be more comfortable breaking apart. Iron sits exactly at the point of greatest comfort, the snuggest arrangement of all, held more tightly than anything lighter and anything heavier. Everything in the universe, pushed slowly enough and left alone long enough, drifts toward that one most settled state. Iron is simply what perfect contentment looks like for matter. So across spans of time that make the ages of stars look like a single afternoon, the cold, dead stars slowly, atom by atom, tunnel their way toward iron. The carbon and oxygen of a white dwarf's crystal, the lighter elements throughout these frozen relics, inch by inconceivable inch toward that final, stable form. Every dead star in the universe is very gradually turning into a ball of iron. Nothing is pushing it there. Iron is simply where matter comes to rest when given enough time and nothing to disturb it. The time scale here is so vast it stops being a number and becomes something closer to a poem about patience. If you sat beside one of these dead stars and watched, you could wait a length of time next to which the entire current age of the universe is less than a single heartbeat, and see essentially nothing change. The star that fuses hydrogen furiously in the sky tonight does in 1 second more nuclear reactions than a cold, dead star will manage across almost the whole of this future era. The fire has not gone out. It has only slowed until each spark is separated from the next by an eternity. What draws me to this is how it quietly rhymes with where we began. The very first act of this story was about how the smallest stars burn so slowly that none has ever finished. Here, at the opposite end of everything, is the same theme carried to its limit, a fire so slow that a single flicker of it can outlast the entire bright history of the cosmos. Slowness, it seems, is not the absence of activity but a form of endurance, and the things that last longest are always the ones doing the least, most gently, for the longest time. It moves me, this idea of a fire that never quite dies. We began with stars burning bright and fast, spending themselves in a rush of light. And here, at the far cold end of everything, the same process still flickers, so faint and so slow, that a single fusion might be the only thing to happen in a region of a dead star for an age longer than all of recorded history multiplied beyond counting. The universe never fully stops working. It only turns the flame down and down and down, without ever quite reaching zero. But this patient drift toward iron is not the quiet ending it might seem. Because as a dead star slowly converts itself into iron, something is building inside it. A change in what the star is made of that cannot go on forever without consequence. A ball of iron at the heart of a dead star is a different thing from the carbon and oxygen it replaced. And for certain stars, the heaviest of these frozen relics, that difference leads somewhere no one would ever expect a long dead star to go. Now we come to the strangest event in the whole future of the universe. A star that died ages ago, that cooled and crystallized and sat dark and silent for a span of time beyond all reckoning, suddenly explodes. Not all of them, only certain ones, the heaviest of the dead. But those few will detonate with the fury of a supernova, in a universe that has been dark and cold for longer than words can hold. The last fireworks of all time, lit by corpses. To see how a dead star could possibly explode, we have to follow the iron. A white dwarf, remember, lost its heat long ago, so heat is not what holds it up. It is held against its own crushing gravity by a stubborn resistance of the particles packed inside it, a rule that refuses to let them be squeezed any tighter. That resistance has a limit, though. If you pile too much mass onto a white dwarf, the gravity grows so strong that even this resistance gives way, and the star collapses. That limit is one of the most important numbers in astronomy, a ceiling on how heavy a white dwarf can be. Ordinary white dwarfs sit safely below that ceiling, and so they never collapse. A dead star with less than the limiting mass simply endures, held up forever by that internal stubbornness. This is the fate of most white dwarfs, including the one our own sun will leave behind. They stay below the line, and nothing dramatic ever happens to them. They cool, they crystallize, they drift toward iron, and that is all. But recall what the slow, cold fusion is doing over those unfathomable ages. It is turning the star's carbon and oxygen into iron. And here, a subtle thing happens that tips certain stars over the edge. Iron is packed more tightly than the carbon and oxygen it replaces. As the star converts to iron, it settles and shrinks a little, growing denser at its heart. For most white dwarfs, this changes nothing important. But for the very heaviest ones, those already sitting just beneath the fatal ceiling, the slow turn to iron is enough to push them over it. Picture a dead star that has spent an eternity converting itself to iron, its core growing gradually denser as it goes. Grain by grain, over spans of time that dwarf everything, it creeps toward the limit. And then, at last, some final atom tips the balance. The star can no longer hold itself up. The stubborn resistance that supported it for an eternity finally fails, and the whole star begins to collapse inward on itself. What happens next is a kind of runaway, and it rewards following slowly. As the star collapses, its core is squeezed harder than ever, and the squeezing drives its temperature up with astonishing speed. For a star made of ordinary fuel, this would simply reignite the fire. But there is a twist here that makes these particular deaths so violent. A normal star, when its core heats up, expands and cools itself down, steadying the burning. A white dwarf cannot do that. Held rigid by that stubborn inner resistance, it does not expand when it heats. So the temperature climbs and climbs with nothing to check it, the reactions racing faster and faster, until in a single runaway instant, a huge fraction of the star fuses at once and blows itself to pieces. This is a supernova, the same violent death that heavy stars suffer today, but arriving in a universe unimaginably old and cold and empty. As the iron core collapses, it releases a torrent of energy, and the star is torn apart in a blinding explosion, flinging its material outward, blazing for a brief while brighter than a galaxy full of the living stars that no longer exist. A dead thing, silent for an eternity, ending its long stillness in a burst of light no eye remains to see. The physicist who worked this out followed the idea with real care, and the numbers he found are staggering even by the standards of this story. Only a narrow band of dead stars are heavy enough for this fate. A white dwarf has to be born near the upper limit to begin with, so that the slow turn to iron can carry it over. By his reckoning, only the heaviest one in every 100 or so would qualify, which across the whole universe still comes to an enormous number of them, something like 1 billion trillion stars destined to end this way. But it is the timing that stops the mind altogether. The first of these dead star explosions will not happen for an almost unwritable span of time. Take the number 1 and follow it with more than 1,000 zeros. That many years must pass before the earliest of these iron white dwarfs finishes its slow conversion and collapses. And the last of them, the final supernova in the history of the universe, comes later still, after a span so long that the number of zeros itself runs into the tens of thousands. There is a plain way to feel the gulf between those two moments, the first of these explosions and the last. They are separated by so much time that the earlier one, unimaginably remote as it already is, sits nearer to us, nearer to this very night, than it does to the final one. The span from the beginning of the universe until now, stretched out and repeated past all counting, would not carry you from the first dead star supernova to the last. Even within the ending of things, there are near ends and far ends, and the distance between them alone is larger than the entire history that came before. Let's try to feel how far away that is, though feeling it may be impossible. Every number we have used so far in this story, The trillions of years for red dwarfs, the vast ages for black holes, all of them are as nothing beside this. If you wrote the age of the universe when the last star explodes, the digits alone would fill pages. The entire era of stars, the whole bright chapter from the first light to the last blue dwarf, is not even the faintest scratch at the very start of that number. These final explosions happen in a future so remote that all of cosmic history until now rounds to zero before it. And picture what one of these explosions is truly like, alone out there. A supernova is one of the most violent events the universe can produce, a flash that can briefly outshine 100 billion stars. But this one erupts into total darkness. There are no other stars anywhere near, no galaxies to light, no witnesses of any kind. A dead star that has been cold and black for longer than the mind can hold suddenly blazes with the light of a galaxy, pours that light out into an empty and endless night, and then fades back into darkness, having illuminated nothing but the void. There is something almost unbearably lonely in that image, and yet something magnificent too. The universe, long after it seemed to have ended, long after the last warmth and the last mind and the last star, is still capable of one more act of grandeur. It saved a handful of explosions for the very end, hid them inside the coldest corpses, and set them to go off across a darkness so vast that no two of them will ever be seen together. The final gestures of a universe performing, at last, entirely for itself. But that phrase, that no two of them will ever be seen together, hides something we have not yet faced. Why could they never be seen together? Even in an empty universe, you might think that a flash bright as a galaxy would be visible across great distances, that these last explosions might at least light each other's skies. They will not. And the reason reaches back to the expansion that has been quietly shaping this whole story, and it makes these final fireworks something even stranger and more solitary than a single explosion in the dark. The reason those final explosions can never light each other's skies is the same quiet force we have kept meeting all along. The expansion of the universe. By the time these dead stars begin to detonate, the expansion will have been at work for so unthinkably long that the universe will have stretched to a size that makes today's cosmos look like a single point. Everything will have been carried impossibly far from everything else. We have to take in just how much expanding happens across the spans of time we are now talking about. Today, galaxies are separated by millions of light years, and even that is hard enough to picture. But expansion compounds, like interest left untouched for ages and over the truly vast timescales before the first dead star explodes, it does not merely add distance. It multiplies it, again and again, until the gaps between objects grow by factors with hundreds of digits. The numbers stop describing anything the mind can render as space at all. A single comparison may help, even if it cannot really contain it. Imagine shrinking the entire observable universe of today, every galaxy we can see, down to the size of a single grain of sand. The distances in that far future era would be as if that grain were then blown up until it dwarfed the whole present universe many times over. That is the kind of stretching we are asking the mind to hold, and even that falls hopelessly short of the truth. So by the time one of these iron-white dwarfs finally collapses and explodes, its nearest neighbor is not millions of light years away, as galaxies are now. It is unthinkably, incomprehensibly farther than that. Each dead star, in that far era, drifts utterly alone, with the nearest other object so remote that no meaningful word for the distance exists. The universe has thinned out until every remaining thing sits isolated in a darkness that goes on, in every direction, past any hope of a neighbor. Now remember the horizon, the boundary set by the accelerating expansion, beyond which nothing can ever reach us. Every object in that far future sits wrapped in its own such horizon, a sphere of possible contact beyond which the rest of the universe is receding too fast to ever be touched. And by that late era, the expansion has pushed nearly everything past nearly everything else's horizon. Each dead star is not only alone, it is sealed inside its own tiny pocket of reachable space, with every other object already fallen forever beyond the edge. So when one of these stars explodes, its light races outward as light always does. But there is nowhere for that light to arrive. The nearest other dead star is so far away and receding so fast that the light can never cross the gap. The expanding space between them stretches the light, draining its energy, reddening it and dimming it, spreading its waves longer and fainter, until long before it could reach any other object, it has been thinned into nothing a detector could ever register. The way space drains a beam of light is gentle rather than violent, and it helps to picture it. Light travels as waves, and as the space the light is crossing keeps stretching, the waves are stretched along with it, pulled longer and lower and weaker. A beam that left as brilliant visible light slides down through red, then into warmth too faint to see, then into something fainter still, losing energy at every step to the growing gulf it is trying to cross. Nothing attacks the light. The space it moves through simply opens beneath it faster than it can advance, and it fades on the way. The flash goes out, blazing as bright as a galaxy, and simply dissolves into the growing dark. This is what makes these last explosions so strange and so unlike any event we know. A supernova today is seen. Its light crosses space and reaches telescopes, other stars, other worlds. It is part of a connected universe where things can still signal to one another. But these final supernovae happen in a universe that has come apart, where every remaining object is causally cut off from every other, sealed in its own shrinking island of reachable space. The explosions cannot be seen by anything. The trouble is not merely that nothing is looking. The very possibility of one thing observing another has been taken away by the expansion itself. Let that distinction settle, because it is a deep one. We are not merely saying no one is around to watch. We are saying something stronger and stranger. Even if, by some impossibility, another observer existed at the nearest possible spot, they still could not see the explosion, because its light will never, can never, reach them. The event and any possible witness are separated not just by distance but by the structure of the universe, each locked in a region the other can never enter. These explosions are unwitnessable in principle, not merely in fact. A strange philosophical weight rests on that, and it deserves a gentle touch. We are used to thinking of an event as something that happens in a shared world, where in principle it could be observed, recorded, known. These final explosions break that assumption. They happen. In the fullest physical sense, matter really does collapse, energy really does pour out, and yet they happen in perfect isolation, unable to affect or be known by anything else in existence. An event that occurs completely and cannot in principle be part of any other thing's story. I keep turning this over because it presses on what we mean when we say something happened. On Earth and all through the universe we know, happenings are woven together. One thing touches the next, Light carries news outward, and events belong to a shared fabric. These last supernovae are the first happenings in the history of the universe to be truly, permanently alone, each one a complete event that leaves no trace anywhere beyond itself. A story with exactly one page and no reader. Maybe this is why the simple act of looking up feels, to me, quietly precious. We live in the era when things can still be seen, when the light of a distant event can still cross the space between and land in a waiting eye. That connectedness, the plain fact that one part of the universe can witness another, is not a permanent feature of existence. It belongs to this early, gathered age, while things are still close enough to reach one another. To see anything at all, ever, is to stand inside a brief window when the universe is still holding together. And picture the whole scene across that unimaginable era. Scattered through a darkness of incomprehensible size, separated by gulfs that dwarf everything, a handful of dead stars flare up, one here, one there, across spans of time as vast as the spaces between them. Each blazes for a little while with the light of a galaxy, alone in its own sealed pocket of night, pouring brilliance into a void that swallows it whole, and then goes dark again, having touched nothing and been seen by nothing. The last light-making events in all of time, each one a private, silent, perfect flare. It would be easy to hear all this as unbearably bleak, and I understand that. But there is another way it settles, if you let it. The last acts of the universe are no less real for having no audience. These explosions lose none of their reality, none of their magnificence, for happening unseen. A flash bright as a galaxy is a flash bright as a galaxy, whether or not any eye receives it. And there is a kind of dignity in an event that is complete in itself, needing nothing outside to make it so. The universe ends its long story of light without any plea to be watched. It simply does the thing fully and lets the dark have it. Still, all of this rests on our numbers holding, on the timescales and the physics carrying faithfully across spans so vast that no experiment could ever check them. And that raises a question we have circled but not yet asked directly. When the times involved are this enormous, when we speak of ones followed by thousands of zeros, does anything unexpected creep in? Could the sheer scale of the waiting allow something strange, something that only becomes possible when you give the universe truly limitless time? As it happens, it can, and it is one of the eeriest ideas in all of physics. A strange idea in physics only shows its teeth when you allow truly limitless time. Over ordinary spans, it stays hidden and harmless. But stretch the clock far enough, past the last star, past the last explosion, out into a future with no end at all, and it begins to suggest something that unsettles even the physicists who take it seriously. The idea is simple to state. Wait long enough, and things come back. It starts with a piece of reasoning more than a century old, from a mathematician studying how systems change over time. He proved something surprising about any closed system left to itself. If a system has only so many possible arrangements to pass through, and you give it long enough, it must eventually return to very nearly the state it started in. Nothing guides it back. With limited arrangements and unlimited time, it simply has no choice. Sooner or later, it wanders back through a configuration almost exactly like one it held before. A gentle way to picture it is a deck of cards shuffled over and over. There are only so many orders the cards can take. Shuffle a few times and you will never see a repeat. But shuffle for an unimaginably long time, never stopping, and eventually the exact order you began with must come up again, purely because there are only so many orders and you have tried so many. Given endless shuffling, every possible arrangement returns, again and again. The cards have nowhere else to go. And here the leap turns unsettling. The universe, in its cold, empty final state, might be a little like that deck. Even in that near-perfect stillness, the faint warmth of the horizon we spoke of keeps things from being utterly frozen. At the tiniest scales, particles still flicker into being and vanish, the vacuum itself never quite silent, forever twitching with the smallest random fluctuations. And random fluctuations, given endless time, will eventually stumble into arrangements that are far from random. Follow that thought, and it leads somewhere dizzying. If empty space is always faintly fluctuating, and you wait long enough, unimaginably long, then those fluctuations must occasionally, by sheer chance, assemble themselves into ordered things. Most of the time they produce nothing, a stray particle here, a flicker there. But once in an almost endless while, they might come together into something startling. A cloud of gas. A patch of structure. In principle, given enough time, anything that is physically possible at all. And this is where the idea turns truly strange, and where physicists themselves grow uneasy. Among the things such fluctuations could in principle assemble, given limitless time, is a working brain. A fully formed structure, complete with a moment of experience, memories, the sense of a whole life behind it, flickering into existence out of the random twitching of the void, and then, almost instantly, dissolving back into nothing. Physicists have a name for this unsettling possibility. A mind born purely of chance in the empty dark. It sounds absurd, and in a way it is meant to. But the reasoning behind it is hard to dismiss, and that is exactly what troubles people. If the universe really does last forever in a faintly fluctuating state, then over infinite time, these chance-assembled minds would form. Rarely. Yes, unimaginably rarely. But forever is a long time, and rare events, given forever, happen not once but endlessly. Across an infinite future, the number of minds flickering randomly out of the void would be, in the cold logic of it, without limit. And now the disturbing part arrives, the one that makes this more than a curiosity. If such minds form endlessly across eternity, they would vastly outnumber minds like ours, minds that arose the slow way, through stars and planets and the long labor of life. There is only a brief early window in which the ordinary kind can appear, while stars still shine. But the random kind can appear forever. So, if you simply counted all the minds that ever exist across all of time, the overwhelming majority would be these fleeting accidents of the void, not beings like us at all. And there is a sharper edge to it that makes the puzzle bite harder. A lone, flickering mind, complete with a lifetime of false memories, is a far simpler thing for the void to assemble by chance than an entire universe of galaxies and stars and worlds. The smaller and simpler the pattern, the more often blind chance can stumble into it. So if minds can appear from fluctuations at all, the cheapest, most common way to make one is to conjure a single brain alone in the dark, not to build a whole cosmos and let life arise inside it the long way. So the random minds should not only outnumber us, they should outnumber us overwhelmingly, by a margin as vast as the difference between assembling one small thing and assembling everything. The reason that should bother us is subtle. If almost every mind that ever exists is a random flicker with false memories of a life it never lived, then, by sheer numbers, you should expect yourself to be one of them. A momentary pattern, convinced it has a past, about to dissolve. The fact that you feel real, that the world around you seems stable and coherent, is exactly what such a flickering mind would also feel in its single instant of existence. The reasoning, followed strictly, undercuts your confidence that you are the ordinary kind of observer at all. But it matters to be plain about how physicists treat this. Almost no one believes we are these random minds. The point of the whole argument, for most physicists, is the reverse. When a line of reasoning leads to a conclusion this absurd, it is taken as a warning, a sign that something in our assumptions is wrong. When a theory predicts that these flickering minds should dominate, that prediction is treated as evidence against the theory rather than as a claim about reality. The strangeness is a tool, a way of testing ideas by following them to where they break. I find something reassuring in that, oddly enough, rather than something to fear. A field that could not notice its own absurdities would be the one to worry about. That physicists can follow their best theories all the way out to a conclusion this strange, recognize it as a warning, and turn back to question the assumptions is a sign the reasoning is honest. The flickering minds are not a prophecy hanging over you tonight. They are a lantern held up at the far edge of the map, showing exactly where the solid ground of what we know gives way. This may be one of the most quietly honest corners of all of science. Here, physics reaches the far end of its own reasoning and finds something it does not like, something that signals the edge of what it understands. Rather than hide that, physicists hold it up and say, in effect, our picture cannot be complete because taken to its limit, it gives nonsense. The random mind puzzle is not really a claim about the future. It is the universe's way of showing us the boundary of our own current knowledge, a place where the map we have simply runs out. And that boundary deserves a pause because it changes the tone of everything that follows. Up to now, we have spoken of the far future with a certain confidence, tracing dead stars and explosions and the slow drift toward iron. But out here, at the very edge, our certainty thins. The timescales grow so vast, the conditions so far beyond anything we can test, that our theories begin to strain and contradict themselves. We are no longer describing the future so much as admitting how little we truly know about it. So we arrive at a humbler kind of question, and it is the one the rest of this journey turns toward. If our confident story eventually dissolves into uncertainty, if even the meaning of time and event grows slippery at the end, then what, if anything, can we still say about the true final state of the universe? When the stars are gone, and the explosions are spent, and even our physics falters, is there any way to speak about the end at all? Every ending we have followed so far shares one thing. It is patient. The last red dwarf, the cooling remnants, the black holes waiting out eternity, the final dead star explosions, all of them unfold across spans of time so vast the numbers lose meaning. But there is another possible ending, one that would ignore all of that patience entirely. An ending that could arrive tonight, or a billion years from now, or never, and give no warning at all. To understand it, we have to look at something we have quietly taken for granted this whole time. Empty space. We tend to think of empty space as simply nothing, a blank stage on which things happen. But in modern physics, empty space is not nothing. It has properties, an energy of its own, a set of values that shape how everything within it behaves. The vacuum, as physicists call it, is a real physical state. And like any physical state, it can in principle be more stable or less stable. Here we can borrow a simple picture. Imagine a ball resting in a valley between hills. It sits there, still, apparently settled. As long as nothing disturbs it, it will stay put indefinitely. We would call that a stable resting place. But suppose the valley it sits in is not the lowest one around. Suppose there is a deeper valley on the other side of the hill, a lower place the ball has not reached because a ridge stands in the way. The ball looks settled, but it is not truly at the bottom. It is only resting in a dip, with somewhere lower it could still go. Physicists have a name for a resting place like that, one that seems stable but has a lower state hidden beyond a barrier. They call it a false vacuum. And the unsettling possibility is that the empty space of our universe, the very vacuum we live in, might be sitting in exactly such a dip. Stable to all appearances, holding steady for billions of years, yet perhaps not truly at the lowest possible state, with a deeper valley waiting on the far side of a ridge we cannot see. If that is so, then our vacuum is living on borrowed time, though the loan may run for eras. Remember tunneling, the trick that let particles slip through barriers they could not climb. The same thing can happen to the vacuum itself. Given enough time, a tiny patch of space could tunnel through the ridge and drop into that deeper valley, settling into a lower, more stable state that our universe had never reached. And once one small patch makes that jump, it does not stay small. This is where it becomes frightening in a way none of the other endings are. That patch of true vacuum, having formed, is at a lower energy than everything around it, and so it grows, its edge sweeping outward as the surrounding false vacuum tumbles into the deeper state too. The boundary expands like the edge of an opening bubble, racing outward in every direction. And it races at the speed of light. Nothing moves faster than light, so nothing could ever outrun it, and nothing could ever see it coming. Let that settle, because it is the strangest feature of this ending. A bubble of true vacuum expanding at light speed cannot be detected before it arrives, even in principle. Any warning would have to travel faster than the bubble to reach you first, and nothing can. The wall of the bubble and the light that might announce it move together, side by side, arriving at the very same instant. There is no flash on the horizon, no distant sign, no moment of dread. One instant everything is as it always was, and the next, without any lead-up, the bubble is simply here. And inside the bubble, the universe is not the one we know. The vacuum sets the rules for everything, the strengths of the forces, the masses of particles, the way matter can hold together. In the deeper vacuum, those rules would be different. Atoms as we know them might not be able to exist. The delicate balances that let matter form stars and planets and living things would be rewritten. Whatever the new state allows, it would almost certainly not allow us, or anything like the ordered universe we have spent this whole journey exploring. This is exactly the kind of idea that can frighten more than it should, so it is best handled plainly. What we know is limited, and better stated straight than dressed up. This is a possibility, not a prediction. We do not know whether our vacuum is truly the lowest state or only a dip. Certain measurements of the particles we have studied hint that our vacuum might be balanced near the edge between the two, neither clearly safe nor clearly doomed. But those hints rest on assuming we already know all the particles and forces there are, which we very likely do not. The honest position is that we simply cannot yet say. It is fair to wonder where such a hint would even come from, since no one can peer into the shape of the vacuum directly. The clue comes from weighing a few of the heaviest particles we have found and seeing how they balance against one another. The masses we measure feed into a calculation of how deep our valley really is and how high the ridge around it stands. When the numbers are put in, our vacuum comes out sitting very near the dividing line, close to the border between a valley that is truly lowest and one that is only a resting dip. It is not a comfortable margin, and it is not a clear verdict either. Nature seems to have placed us, as far as we can measure, right on the knife's edge between safe and not, which may mean something deep or may only mean our measurements are not yet fine enough to tell. And even if our vacuum is only a dip, the weight would almost certainly be immense. The kind of tunneling required is so unlikely that the expected time before it happens is vast beyond the ages of stars, longer, most likely, than nearly everything else in this story. The point is not that this ending is near. Almost certainly it is not. The point is stranger and quieter. Of all the endings, this is the only one that carries no schedule, that could in principle interrupt any of the others without notice. Something oddly freeing lives in that thought, once the fear passes and I find myself returning to it. Every other ending we have traced is a certainty deferred, a fate we can see coming from an unthinkable distance. This one, by contrast, cannot be seen coming at all. And so, in a strange way, it asks nothing of us. There is no watching for it, no preparing, no dread that could ever be timely. If it comes complete, with no before and no after that anyone experiences. It is perhaps the most painless ending imaginable, precisely because no one could ever know it had begun. And this is the thing I would gently hand you if you are lying awake with it. An ending that gives no warning is also an ending you never have to wait for. The same wall of light that would arrive without notice also means there is nothing to watch the sky for, nothing to fear on any particular night, because a danger you cannot see, cannot prepare for, and would never feel is, for all practical purposes, no burden to carry at all. It changes nothing about tomorrow, or the breath you are taking now. The universe, if it holds such a bubble somewhere in its future, keeps it entirely to itself, and leaves this quiet night wholly untouched. So we have now gathered several possible ends, and they do not all agree. The slow drift of the patient endings, the flickering uncertainty at the edge of our knowledge, the sudden silent bubble that keeps its own counsel. Faced with such different pictures, a fair question rises. Is there any way to step back from all of them? To ask not how the universe ends in this scenario or that, but what happens to the very ideas of time and ending when there is truly nothing left? One thinker took that question further than anyone, and where it led him is the strangest turn of all. Suppose we follow the patient endings all the way down, past the last star, past the last explosion, past the slow evaporation of the black holes. Eventually, in that picture, almost nothing is left but radiation, faint light drifting through an unimaginably vast and empty space. No stars, no planets, no matter of the ordinary kind, only a thin bath of light growing ever colder and more spread out. And here one thinker noticed something that changes how we might understand that ending altogether. To feel his idea, we have to ask a question that sounds almost too basic to matter. What does it take to measure time? Or distance, for that matter. We measure time with clocks, and every clock, at bottom, is something that changes at a steady rate. A pendulum swinging, a crystal vibrating, an atom ticking through its states. To have a clock at all, you need something that can mark one moment as different from the next. You need change, and something to do the changing. And here the subtle thing appears. Not everything experiences time in the same way. Particles that have mass, like the ones you are made of, move slower than light and carry a kind of built-in clock, a rhythm that lets them mark the passage of time. But light itself, a massless particle, does not. A particle of light experiences no time at all. For it, the moment of its creation and the moment of its absorption, however far apart to us, are the same instant. Light does not age. It carries no clock. This is not a poetic way of speaking. It comes straight from how time behaves for anything moving very fast. The nearer a thing comes to the speed of light, the more slowly its own inner clock runs, as seen by the rest of us. A particle of light rides at that speed exactly, so its clock does not merely slow. It stops. Between leaving a distant star and landing in your eye tonight, a beam of starlight has, from its own point of view, spent no time whatever, the whole journey folded into a single timeless instant. So imagine a universe with nothing left in it but light. No massive particles, none of the things that carry an inner rhythm, only massless radiation drifting forever. In such a universe, there would be nothing left that experiences time. Nothing that ages, nothing that ticks, nothing that could mark one moment as different from another. And if nothing can mark the passage of time, then in a real sense, time itself loses its meaning. There is no clock anywhere to say that it is passing at all. The same strange thing happens to distance. To measure a distance, you need rulers, and rulers are made of matter, of atoms held at fixed sizes. In a universe of nothing but light, there are no rulers either, nothing of a fixed size to measure against. Without matter to provide a scale, the very notions of large and small begin to blur. A vast cold emptiness and a tiny dense point might, without any ruler to tell them apart, become impossible to distinguish. This is the doorway to the idea, and it is a truly startling one. Zwithinker, who followed it, argued that the far future of our universe, cold and empty and full of nothing but light, might be, in a precise mathematical sense, indistinguishable from the hot, dense state at the very beginning of a universe. Not similar. Indistinguishable. If there are no clocks and no rulers, then the enormous cold emptiness of the end and the searing compact fire of a beginning could be, mathematically, the very same state, just described in two different ways. Let that land slowly, because it is a lot to take in. The end of our universe, the final cold nothing after every star and every particle of matter is gone, might be identical, in the deepest structural sense, to the fiery birth of a new one. The end would not be followed by a beginning across some gap of time. The end would simply be a beginning, seen without the clocks and rulers that made it look like an ending. The last cold whisper of one universe, read another way, is the first hot instant of the next. From this, the thinker built a whole vision of the cosmos. It is no longer a single universe with one birth and one death, but an endless sequence of them, each vast era of expansion and cooling flowing seamlessly into the hot beginning of another. Cycle after cycle, without first or last, each one's cold, empty ending serving as the next one's blazing start. A universe that does not end so much as forget its own scale and begin again. It matters to be honest about where this sits in physics, more than to have a tidy story. This is not a mainstream view. It is the idea of one deeply respected thinker, taken seriously by some and doubted by many. It rests on assumptions that not everyone accepts, above all the assumption that in the far future every particle with mass truly vanishes, leaving nothing but light. Some searches have been made for faint marks such cycles might leave in the sky, and the results remain disputed, without the clear confirmation that would settle the matter. The reasoning behind those searches is quietly clever, all the same. If a previous cycle really did flow into ours, then violent events in that earlier era, whole galaxies of black holes colliding, might have left the faintest rings or ripples stamped into the oldest light we can see. A few researchers believe they have glimpsed such patterns. Most who have looked are not convinced the patterns are real rather than chance. So the door stays open a crack, neither shut nor clearly ajar. This is a possibility at the frontier, not an established fact, and it should be held with that lightness. But even held lightly, it does something valuable to the whole shape of our story. Every ending we have traced has felt, in its way, final. The cold, the dark, the silence, the last light dissolving into the growing void. This idea offers a different frame, less a consolation than a real question. What if what looks like an ending depends entirely on standing outside it with a clock and a ruler in hand? And what if, from within, with no clock and no ruler left anywhere, the words ending and beginning simply cease to mean different things? Something clarifying lives in that, quite apart from whether it proves true. We have spent this whole journey measuring, counting years, comparing sizes, laying vast numbers against small human spans. This idea quietly reminds us that all of that measuring depends on us, on having instruments and minds to do the measuring. Strip those away, and the universe does not necessarily contain an ending in the way we imagine. It may contain only change, which we, with our clocks, choose to read as beginnings and ends. A gentle humility settles over that thought, the longer I stay with it. We are the ones who divide the flow of things into starts and finishes, births and deaths, because that is how a creature with a lifespan and a heartbeat has to see the world. The universe itself may keep no such ledger. What feels to us like a final darkness might be, to a cosmos with no one counting, simply another passage, no more an ending than the turning of a page is the end of a book. The finality we fear may be, in part, a shape our own minds cast onto something that neither begins nor ends the way we do. So we have come a very long way, from the last small star flaring blue, through frozen crystal cores and patient black holes, to explosions no one can see and endings that may loop back into beginnings. And all of it, every scenario, has been a description of things out there, far away, far in the future. But there is one more turn this journey has to take, and it is the closest one of all. After looking so far outward, into the deepest reaches of cosmic time, we need to come back to something very near, something happening in you, right now, as you listen. We have thrown around some staggering numbers on this journey, and before we come home, it is only fair to stop and ask a plain question. How much of this do we truly know? Not merely believe, not merely calculate, but know the way we know the sun will rise tomorrow. The honest answer sorts everything we have discussed into a few very different kinds of certainty, and seeing those differences clearly is its own kind of gift. At the firk, that the universe is expanding and expanding faster over time, that distant galaxies are slipping away, that the afterglow of the beginning still fills the sky and is cooling, that white dwarfs crystallize as they age, which we confirmed by finding them piled up at just the brightness the freezing predicts. These are not stories about the far future. They are features of the present, checked against the sky, and we can hold them with real confidence. A step less certain are the things we infer, the conclusions we draw by taking physics we trust and following it forward. That a red dwarf will burn for trillions of years, that the last stars will flare blue before they die, that black holes will eventually evaporate. We have never watched any of these things happen, and never will. But they follow from the same well-tested physics that describes the stars we can see, wound forward like a reliable clock. We do not know them the way we know a measurement, yet the reasoning is sound and the ground beneath it firm. And then, at the far end, are the ideas that live purely in theory, stretched so far beyond anything we can test that we hold them differently altogether. Whether protons decay, whether dead stars will one day explode, whether the vacuum is stable, whether cycles repeat, whether random minds flicker in the void. These are not idle guesses. They follow carefully from serious physics, but they reach into conditions so extreme and time so vast that no experiment could ever confirm them, and we should hold them lightly as the best reasoning we can manage about places we can never visit. To feel just how far our confident numbers outrun anything we have checked, consider the longest span of time we have ever measured. Not calculated, not predicted, measured by watching something happen. It comes from a particular kind of atom, a form of the element tellurium, that is very slightly unstable, decaying so slowly that its half-life, the time for half of a sample to change, is enormous. How enormous? Something like 1 trillion years. A 1 followed by 24 zeros. That is the longest decay time human beings have ever directly measured, teased out by watching a vast number of these atoms and catching the exceedingly rare few that change. It is a triumph of patience and care, one of the slowest processes we have ever managed to clock. The way such a thing is measured at all is quietly beautiful, and it echoes the trick we met with the protons. You could never watch a single tellurium atom and hope to catch it changing, since you would wait 1 trillion years on average for one event. So instead, you gather an enormous number of them, more atoms than there are stars in 1,000 galaxies, and watch the whole crowd at once. In a large enough sample, even a change that any single atom performs only once in 1 trillion years happens often enough, across the crowd, to be seen and counted in a human lifetime. The vastness of the weight is paid for once again by the vastness of the numbers. Now set that against the numbers from our story. 1 trillion years is already almost incomprehensible, 100 trillion times the current age of the universe. And yet it is nothing, less than nothing, beside the timescales we spoke of for the last dead star explosions. Those came with a 1 followed by thousands of zeros. Our longest measured time has 24 zeros. The explosions have thousands. The gap between what we have measured and what we have calculated is itself so vast that no ordinary comparison can hold it. To make it plainer, try laying the two side by side. If our longest measured time, that trillion years, were shrunk to the width of a single human hair, then the time until the last dead star explodes would still be a length no line could draw, running off past the Earth, past the stars, past the edge of everything we can see, and not stopping. One of these numbers we have touched with real instruments. The other we have only reached with the mind. Let that sink in for a moment, because it is humbling in the best way. When we speak of protons decaying, or dead stars exploding, or the universe cycling, we are reasoning about spans of time so far beyond anything we have ever witnessed that the longest process we have measured is, by comparison, instantaneous. We are like someone who has carefully timed the fall of a single raindrop and then tries to describe the lifetime of a mountain range. The reasoning may be perfectly sound, but the distance between our evidence and our conclusions is a chasm that deserves respect. What moves me is that we reach across that chasm anyway, and reach honestly. A creature that lives for a few decades on a single small world has somehow worked out the birth and death of stars it will never see, using nothing but careful thought and patient looking. We cannot cross the distance to those far futures, and we know we cannot. Yet we can still map them, mark clearly where our knowledge is solid and where it thins to guesswork, and hold the whole picture with open eyes. There is a quiet courage in that, in describing an ending you will never witness and being scrupulously honest about how much of the description you can trust. This is not a reason to distrust the science. It is a reason to hold it honestly. The physicists who work out these far futures are not pretending to certainty they lack. They label carefully what is measured, what is inferred, what is speculative. And they change their picture whenever a new measurement demands it, as we saw when the discovery of acceleration overturned an older hope. That willingness to say we are not sure, and to spell out exactly how unsure, is not a weakness of the science. It is the very thing that makes it trustworthy. And there is something freeing in accepting that we do not know the ending, not really. We have sketched several possible ends, and they do not agree, and we cannot yet say which is true. The universe has not shown us its final page, and it may be that no one who could read it will ever exist. Rather than a failure, this feels to me like an open door. We are living in the middle of a story whose ending is still truly uncertain, and there is a kind of aliveness in that, in belonging to a chapter early enough that the last one has not been written. So this is where our long journey outward finally turns back. We have gone as far as physics can currently take us, to the very limits of what can be known, and found, at the edge, a frank and honest uncertainty. The universe is vast beyond measure, old beyond feeling, and its ending is hidden from us behind spans of time we can calculate but never cross. We have followed the last star into the dark and kept going, past everything, to the ragged edge of knowledge itself. And after all that reaching outward, there is one small thing left to notice, and it may be the most surprising of all. Every enormous process we have traced, the burning of stars, the cooling of remnants, the slow slide of the whole universe toward its end, is built from a single simple event, repeated beyond counting. Energy moving from somewhere warmer to somewhere cooler. That one quiet event is the engine behind all of it. And that very same event is happening right now, in the dark, a few inches behind your eyes, as you lie here listening. When you look at a star, something small and quite wonderful happens. A particle of light that left that star long ago, after crossing a distance you could never walk in 1,000 lifetimes, ends its whole journey inside your eye. It strikes a single molecule tucked in the back of your eye, and that molecule, catching the light, bends into a slightly different shape. That tiny bending is the beginning of seeing. From it, a signal travels inward, and a star, impossibly far away, becomes a point of light in your mind. Notice, gently, how little it takes. A fully dark-adapted eye can respond to a mere handful of light particles, and each molecule that catches one needs only that single particle to do its work. One particle of light, one molecule, one small change of shape. That is the entire physical event of seeing a star. Everything else, the wonder, the recognition, the quiet ache of looking up, is built on that one small bend. And think about what that light carried to reach you. It set out from the surface of a star, from a fire fed by the same slow flow we have followed all night, and then it traveled, untouched and unaging, for years, sometimes for thousands of years, across an emptiness with almost nothing in it. All that way, holding its little parcel of energy, until the one moment it met a molecule shaped exactly to receive it. The starlight did not fade or tire on the journey. It waited, in its own timeless way, for the single meeting it was made for, and gave itself up completely in the instant it arrived. And this is the thread that ties the whole journey together, gently, at the very end. That bending molecule is powered the same way everything in this story has been powered. Light arrives carrying energy from the hot star that made it, and it gives that energy up to the cooler molecule waiting in your eye. Energy flowing from something warmer to something cooler, doing a little work as it passes. The very same event that turns a water wheel, that lets a mind think, that lit every star and will govern the last cold ember. Seeing a star is one more instance of the single process the whole universe runs on. Take that thought outward for a moment. The star burns because energy flows from its hot core to cold space. That flow sends light across the dark. The light crosses the years and reaches you. It gives up its energy to a molecule in your eye. Every step, from the heart of the star to the back of your eye, is the same flow from warm to cold, the same gentle falling of energy, from where there is more to where there is less. You are not separate from the process we have been tracing across all of time. The great flow does not run out there in the cosmos while you watch from somewhere outside it. It runs through you as surely as it runs through the star. You are, right now, a place where it is happening. That is what it means to be alive in the era of stars. We have spent this whole journey learning how rare and brief this era is, how the age of starlight is only the faintest opening scratch at the very start of the universe's long life. And we are here for it. Not in the cold, dark aftermath, not in the endless, dim future of drifting embers, but now, while the stars are still lit, while their light still crosses the dark and finds waiting eyes. Something in that is quietly steadying, if you let it. Every star you have ever seen was pouring out its light for ages before you looked, and will pour it out for ages after. The ones scattered across the sky tonight are not near their ends. They are in the fullness of their lives, burning steadily, with most of their fuel still ahead of them. The night sky, thick with stars, is the universe in its brief, bright morning. And you happen to be born early enough to stand beneath it and see. and you are far from the only one who ever has. The same starlight that reaches you tonight reached everyone who has ever lived, every person who ever tilted their head back and wondered, across every age and every land. They saw very nearly the stars you see, lit by the same slow fire, arriving by the same long fall of energy from warm to cold. To look up is to join a quiet company stretching back as far as there have been eyes, all of us briefly warmed by the same distant light. We began with a question about the very last star, the small red ember that will flare blue and die when the universe is unthinkably old. And we followed the dark all the way down, through cooling remnants and patient black holes, through explosions no eye will see, and endings that may fold back into beginnings. It is a long, strange, humbling road. But it circles back to something close and warm. The same physics that governs that final darkness is the physics letting you see this night at all. So if any of this stays with you, let it be this. The universe is spending its light, slowly, across spans of time we can barely name, and one day, far beyond all reckoning, the last of it will fade. But that is not tonight. Tonight the stars are still burning, and their light is still arriving, and you are still here to receive it. The long story of light is nowhere near its final page, and you are reading it from very near the beginning. Feel, if you can, how gently the process is working in you even now. Your body warm against the cooler air, quietly shedding heat into the room, doing the same thing every star does, letting energy fall from warm to cold. Your breath slowing. Your thoughts settling. All of it part of the same great flow that fills the universe with light and will, in the end, spend that light away. You are not watching the process from outside. You are a small, warm, living part of it, resting here in the dark. And a softness comes with that when you let it reach you at the end of a long day. The warmth leaving your skin into the cool of the room is the gentlest possible version of the thing that lights the stars, so faint and so ordinary that you never feel it as anything at all. You do not have to do anything to take part. Simply by being warm, by breathing, by resting here, you are already inside the same current that carries the whole universe from its bright beginning toward its quiet end. Nothing needs reaching for. You are already home in it. And a deep peace waits in that, if you want it. Not the peace of having answers, since we found, in all honesty, that the ending is still unknown. But the peace of belonging, of knowing that the light in your eyes and the fire in the stars are the same thing, that you are made of the same flow, running the same way as everything that has ever shone. You are not a stranger to this universe. You are one of the ways it briefly wakes up and looks at itself. So let the stars be where they are, far away and burning, in no hurry to end. Let the vast dark future stay far off, where it belongs, untroubling this quiet hour. There is nothing you need to hold on to tonight, nothing to solve, nothing to carry. The universe has been doing this for billions of years without your help, and it will go on gently, whether you are watching or resting. You can let your eyes close. The light will still be there. Thank you for spending this long, quiet journey with me, all the way to the last star and back. It means more than you know to share these hours with someone who wonders about such things. Rest now. The stars will keep burning while you sleep, and there is still so much light left. Good night.